Welcome to APEC Open Mic. It is September 14th, and I'm your moderator, Tim Ventura. I want to give a big thank you to everybody who is joining us on today's Zoom call, along with everybody who is watching us in replay on YouTube. So today's session is for open discussion and ad hoc presentations. We don't schedule presentations in advance. We do have a couple of folks who have stuff to share with us today. So I want to just let you know in advance, we're going to go to that. We are going to start out with introductions. I am really excited about that. This is going to be a round robin. We're going to try and keep this to like 10, 15 seconds if possible. Just, who you are, what you're passionate about, what excites you, your key project kind of a thing. Short, quick, and to the point. Everybody, please have your cameras on. That's something that we're asking now. This helps foster the kind of collaborative working environment that we really want, right? I don't think anybody wants to be in a room full of dark cameras. So we've got that. And then let me start out with a couple of quick reminders. You can view replays of all of our conference sessions, as well as details and speaker info on our website at altpropulsion.com and on our YouTube channel. And actually, that is linked from the website. So also, during our ad hoc presentations, try to save your questions for after the presenter finishes so that we're not interrupting them. Again, things are a little more mellow because it's open mic, but we are trying to be respectful and let people present without too many interruptions. So you can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type your questions into chat. Sometimes those questions scroll up really fast, so we miss them. So raising your hand is the best way to get heard. Again, Option Y on Mac or Alt Y on Windows. We're not firm on hand raising unless things get chaotic, but please use those, if you can. So I think that's pretty much it for now. I'm going to do, let me see, admit all and unspotlight myself. And I think we are pretty mellow. So let me see. Okay. So I did good so far, but they changed Zoom. So now I don't know how to do the view that I need. There we go. Look at that, full house. Got the whole gang here. Okay, so let's do presentations, or sorry, let's do introductions. So I'll on my screen, I'll go left to right. I want to start with Mr. Phil Bouchard. Phil, go for it, sir.
Thanks, Tim. Hi, I'm Phil Bouchard. I've been part of APEC since the dawn of APEC, which is fun. I'm an author of my own theory, and I've got a stack of experiments I'm going to show tonight, which are very interesting. So thank you.
Awesome, Phil. Thank you, sir. Dr. James Woodward, sir, welcome back.
Hi, Tim. Aha, you're not getting me up on the screen full, or maybe you are, and I'm just not seeing it. Jim Woodward, Cal State Fullerton, Mach effects, a way of producing propellantless propulsion based on Einstein's idea that inertial forces are really gravitational forces. And we've got some major milestones or benchmarks in the past year or two that Curtis Horn will be telling you about very briefly.
Oh,
Primarily
wonderful.
primarily due to Michelle Broyles, who's out of the hospital and recuperating in a convalescent home so that she doesn't do anything stupid. And Curtis are the principal contributors to this, and I'm pleased to advance whatever they can for them. Thank you.
Thank you, sir. Let me go to Richard L. next. Richard, go for it.
Can you hear me?
Yeah.
Yeah, mechanical engineer working on over unity, free energy.
Awesome. Okay, well, thank you, Richard. Let me go to HFK next.
Henry, tinkering with magnets, magnetic fields, coils, and MOSFETs.
Thank you, Henry. I'm going to rename you Henry too. That way I don't forget. So my memory sucks for names these days. Let me
That's
go to
okay.
Let me go to Bruce next. Mr. Cornett.
Yes, I am here. My interest is in reverse Doppler and its cause, and that's what I've been studying.
Wonderful, Bruce. Thank you, sir. Let me go to David J next.
There we go. Hi, good evening. David Jenkins, UC Davis Electrical Engineering. I help Jim Woodward occasionally with Mega on doing current and voltage tracking to make the thing in phase so we get continuous thrust out of it.
Wonderful. Well, thank you, David. Let me go to Rick next.
My name is Rick Muller. I'm from New Jersey. I'm a retired materials engineer. I like to come to APEC and learn about various theories and see the experiments. And I'm interested mostly in anti-gravity.
Thank you, Rick. Let me go to Dennis Lee next. Dennis, welcome back, sir.
Thank you. I am Dennis Lee. I am a NSF grantee working on a hypertransfer vehicle, cam drive, and working on proposals for that particular project. Completing my phase one.
Yeah, and actually, Dennis has, just so you guys know, Dennis sent me an email earlier in the week talking about National Science Foundation stuff, and so I sent him the link to this, and in a bit he can tell us a little bit more about it. Let me go to Leonardo next, sir. Okay, mechanical propulsion repeats spaceship basic movement. Okay. Oops, and you're muted, sir.
Now, okay. I'm Leonardo Rivera. I'm an independent researcher. My study is based in this formula.
Okay. Well, and so later on, maybe we can come back to that, and you can tell us more about it after we get through the introductions and all of our entry stuff. So,
Okay.
Let me go to Plasma Baur, Mr. Al Baur. After this, Al.
Yes, Tim. How are you?
Doing well. Welcome back.
Yes, I sent a couple of emails and I didn't get a response. I hope you received my emails. I'm dealing with levitation, electrostatic levitation, and ionic propulsion. What I have today is a couple of videos related to this. And I have also, for John Brandenburg, I made his experiment, which is electromagnetic coil. And I would like to give him the information, maybe some use to him.
Yeah. So Al, if you could forward that to me, I will CC John and I'll forward that on to him. And actually, I just found your email. It looked like it got buried, but I have that. And so maybe we can come back to the videos in a bit. Just hang on to those for a bit when we get through introductions. And then Mark also, I CC'd Mark because Mark was talking about translating your work as well. That is something I've not forgotten. And so let me go to Ron Evans next. Ron, welcome back, sir.
Hello. Can you hear me?
Yes, I can.
Okay, this is England and it's midnight.
I know it's super dark there too. It
is dark. Okay, I'm interested in photon drive and redshift.
Okay, thank you,
That's
Ron.
my latest. Yep.
Let me see. Let me go to one.
Good camera.
I'll do ask to unmute. DUH1. It says DUH1's iPhone. There we go.
Okay. My name is Hong. Good afternoon.
Oh, okay. It's okay. Let me rename you Hong. And then Hong, actually, for you guys, I asked Hong to do a presentation on September 28th also. So I'm going to have him go through. He has a pretty elaborate experiment and theory that he's working on. And so we're going to try and have him in. Okay, let me go to a man who needs no introduction next, Mr. Mark Sokol.
I would just change.
Hey, Mark Sokol here, Falcon Space and co-founder of APEC. I am here at the Falcon Space Lab. We're looking into dynamic nuclear polarization, asymmetric capacitors. Actually got the vacuum chamber up, and a whole load of other experiments, mercury vortex engine. We got a lot of cool stuff going on, and this big valve just arrived. So yeah, exciting night.
Yeah, yeah. Well, and so for everybody who's here, we are planning. I don't know if I should leak this or not. We have our, I think, 4th anniversary coming up for APEC in November, and so we're going out to New Jersey, and that's going to be a working thing. They wanted me to show up late because they said all I do is annoy and interrupt. But I was like, okay, fine, I'll come in a week late and annoy and interrupt, and we'll do the birthday party. So, let me see. It just remixed my people. Let me go to JH next.
Hi, I'm John. I'm a CAD engineer, super interested in the Pius patents and, basically all the topics that everybody knows about that come here.
Okay. And, John, if you want to email myself or Mark, I can, if you have questions about those, I can probably forward those on to Sal. So.
Oh. Okay, awesome.
Yeah. Let me see. Let me go to Mikolaj next. Welcome, sir.
Sorry, I couldn't find my mic. Okay, my name is Mikołaj. I'm validating experimentally that it is possible to build a propeller that works in space. All welcome to prove me wrong or confirm my results. I have very interesting results, and idea is, I think, fairly solid. And I send you a few emails. I would like to eventually present my results and stuff like that. So that's about it.
Okay, yeah, and if it's okay, if you want to resend that email,
I will,
been getting buried. Actually, I'm going to blame a couple of PhD physicists who have been very busy with political stuff this week. So my inbox is just overflowing with junk.
I'll resend it to Mark and David and you because you're on the trail. Okay, so not to APEC. Okay, all right.
Oh, absolutely, absolutely. Yeah. Okay, let me go to Ken L next.
Can you hear me?
Yeah, you sound great, Ken.
My name is Ken Lentz. I am a retired mechanical engineer. I'm working on a bunch of stuff, mostly just learning about what you guys are doing and trying to understand what everybody's doing and seeing if I could help anybody. I've got a lot of experience in places that relate to things that you guys do. And so anyway, within the next few months, maybe I be able to make a presentation too.
Oh yeah, absolutely. Well, again, if you're interested in that, come up with kind of an outline about what you'd like to do and email that in, and then we can try and work it in. I'm actually scheduling for November right now. I've got September is totally full. September 28th is our next StreamYard, and then October 26th after that. And then let me see, around the 20th something in November. So just definitely send it in.
Sure.
Okay.
Let me some of them are short, and I've got a bunch of questions. I'd like to large questions, conceptual questions. I would like to ask some of the experts here, but
okay.
In the form of presentation.
Okay. Yeah. I would say definitely send it in. I think that's more than fair. Just and I think it's totally cool to pose open-ended questions, right? I think that's what honest inquiry. It's not necessarily what it's all about, but I think it includes that, right? Being able to say, look, I don't necessarily know what the answer is. Maybe nobody does, but this is an interesting question. Let me go to Mike next. Mike Choate, sir.
Hi, Tim. Thank you. Yeah, I'm new to APEC. I'm a retired electrical engineer. I had a professional engineer license here in Texas. I specialized in microprocessor technology having to do with primarily reliability and quality and performance. And microprocessor technology. I've been very interested in alternate propulsion for many years, had my own theories for some magnetic related propulsion, but my main interest in the projects at APEC are is anti-gravity and arts parts.
Awesome. Well, thank you, Mike. And before I go to Robert, I should mention you guys all probably know how to use the chat tool. It looks like some folks are already starting to type in that. One of the reasons that we're doing these introductions is to try and help create and firm up our community, right? And this is not Tim, this is not Mark, this is all of us together are a community. And as you guys are speaking, as you're presenting on your ideas and stuff, if you want to communicate together, keep an eye on that chat box. That is a very easy way to contact each other, share emails, things like that. I try not to mention emails on air because we really don't want sensitive stuff like that going out on YouTube, right? But the chat box, it's what happens in chat stays in chat, so to speak. So you guys can communicate pretty freely there, and just be aware that we've got like 35 people in the conference. Everybody can see chat unless you talk specifically to someone else. But if you have questions or you want to share for each other, that is a great place to do it. So okay, let me go to Robert Francis Jr. Sir.
Hi, I'm here to present experimental data on magnet drop experiments and proving one way or the other whether it's altering gravitational mass or inertial mass.
Awesome. And that is well overdue, sir. Well overdue. We've had many, many debates about that. So, okay, let me see. Let me go to Jim next.
Jim Morrison, me?
Yeah. Oh, there we go. You're way back from your computer, but actually that's kind of awesome.
Oh, not me? Okay.
Oh, no, I think it's Jim Morrison.
Is that me?
Yeah. Yeah.
Yes,
in the blue shirt on the couch.
Okay, that's me. I've been working on gravity and alternate energies for about 50 years on and off, and I believe gravity is basically a vortex ether. And I'm working on a prototype for that. And it also integrates consciousness for a control mechanism. I know it sounds crazy, and I'll let you know if it is crazy in a little while. But
awesome. Well, Jim, thank you. And actually, I know that Shiva Mayuchi, he's going to be doing a presentation. He has been talking about something similar, and I've heard several other people talking about this vortex way of visualizing it, right? That's something that I tend to subscribe to as well. And I think Einstein with this metric torsion tensor, right? He kind of alluded to that as well. So,
fascinating.
Yeah.
What started me off on that is I was able to control a rotating storm and hold it in position. So I think could have been a coincidence. Who knows?
Well, thanks again, Jim. Let me go to Mr. Eric Ryder. Sir, welcome back.
Hello, Tim. Yes, so I am Eric Ryder, and I'm the inventor, discoverer of the unquantum effect that looks like it's the only experimental way to show how quantum mechanics fails. It relates directly to what dark matter is and what zero-point energy is. And I have much more material. I gave a presentation at your last APEC, and I have much more in terms of the history, theory, and applications. And I'm wondering if you're interested in hearing me again.
Yeah, Eric, actually, I absolutely am. If it's okay, let me ask you to shoot me an email, and we'll get you on the schedule for StreamYard. If you're open to it, I'd love to have you do another presentation on it.
Great. Thank you.
Absolutely. Okay, let me go to Andrea Radovic, and let me apologize for mispronouncing your name because I always do that.
Okay, yes, Andrea Radovic is correct pronunciation of my name. I want to stress that I'm not in my home and I don't know how good this internet is here. inherited some house from my dead father, and I have to come here for some reason. And I promised it to make presentation, but I didn't because I have some medical issues. I explained this in my email I sent to you. I did some interesting experiments related to electric transformer, and I do believe that all answers related to gravitational mass and inertial mass could be explained by operational electrical transformer, because inductance is closely related to alteration of inertial property of electrons. I found that actually inductance is related to electrons inertia. So we don't have materials in gravitation that correspond to magnetic materials in electromagnetic. So we don't have something like ion in gravitation, but it does not mean that such materials do not exist. Simply do not know that, and maybe they do exist, but somebody excavated this material in the past. Some extraterrestrial civilization, I don't know. But simply, again, my theory is very simple. I can explain again. The magnetic field appears in composition of several electric fields moving with different velocities, and with appliance of Doppler effect, something like magnetic field appears, and this is actually magnetic field. And gravitational field is composition of two rotational magnetic field, and this is pretty good explanation because all known formulas directly can be derived completely correct from these two assumptions.
Okay, and Andre, do you have it might help people if you had, because we're just doing the intros, if you had links, do you have links that you could drop into the chat? And then
practically all of my website, all these and these new experiments are not on my website because I'm preparing some papers from some journals and magazines.
What's your website? Let me put that in so that we can get to the next one.
ANDRIJ Andrea, I send you this. How to spell this? ANDRAJ.
Okay. Yeah, if you could, yeah, or actually, if you could paste that into chat, and then let me go actually to Kendall Smith, and that way we can kind of keep our momentum and get through our introductions. Kendall, welcome, sir.
Greetings. Thank you for calling on me. I'm a newcomer. I'm sort of lurking and listening to the conversations here. I am in the process of relocating and building a shop building, which includes quite a bit of workspace, and I'm basically looking for a project to start into. I'm attracted by a lot of the presentations I've heard about propellantless propulsion systems, and so I'm building a bunch of high voltage supplies and electrostatic instrumentation, and but basically looking for a project. So I'll just work back here and wait.
Yeah, well, and Kendall, very quickly, the person that you may want to talk to is Mark Sokol, because Mark is, I mean, he has a massive lab, and I don't know if you have his email. Mark, maybe you could drop your email into chat and people could reach out there. But Mark has his finger on the pulse of experiments right now. I mean, he's got 5 or 6 going on himself, and there are many others. And so kind of wherever your interests flow, he could probably recommend something. So.
Okay, I see he just put his link in there, so I will reach out to him. Thank you very much.
Kendall, where are you located?
I'm actually in northern side of South Carolina right now.
Awesome. Okay, let me go to Darren next, or Darren's curtains. We'll ask. Let me see if Darren's curtains will introduce themselves. There we go.
Hey, Tim.
Hey, your camera's way too. Can you tilt the camera down a little bit?
Hi.
There we go. Okay.
And I'm signed on to the phone too.
Oh, okay. Okay. Oh, I see. Yeah, I see the beach and the umbrellas.
Yeah,
okay.
That's me. All right.
Okay.
You know me. I just like new stuff, and you've got a lot of new stuff.
Awesome. Okay, well, let me go to Masood Haroni next. Sir?
Hi, my name is Masood.
Welcome.
I have a very specific experiment in mind that I'm not going to say it's going to work, but I like to think that it has a chance. And I've run it by a professor of mine who's actually a professor of mathematics, but he also has a master's in physics. And then I've run it by him, and I run it by a few others. And even though they like the idea, they can't really run such an experiment, because if it does fail, then they're trying something crazy, and that's going to look bad on them if it doesn't work. So I just thought maybe I'd throw it to some crazy people here, see if they wanted to do it for me, since I'm not really good with building things. I'm a I'm a cut twice, measure nonce kind of person. I'm not designed for that, but I am designed for
Yeah, well, I would say definitely put the idea out there, right? I mean, one of the things, and this is just in general, like when people when it comes to intellectual property, because again, everything that we do in APEC is open. And so if you have, quote unquote, secret sauce that you don't want to share, this is not the place to share it, right? Hold back that secret sauce if you don't feel comfortable with it. But for anything that you do want to share or collaborate on or anything like that, this is absolutely the place. And in terms of crazy ideas, it reminds me of that phrase, was it, there are no mistakes, only happy accidents, right? So, you know, that's just about where we're at. Let me go to Brendan next. Sir?
Well, hello, folks. Yeah, I'm Brendan McNamara. I'm a technologist, web designer, writer, graphic artist, ecologist, carpenter, farmer, dad. Currently wrapping up my bachelor's in business and considering either going on to a master's in sustainable design or a bachelor's in physics at ASU, which I'm kind of leaning toward the physics. And I'm super interested in just warp drives, asymmetric capacitance, space-time metric engineering, all that kind of stuff. I don't have any pet projects, although I have my own vague ideas at kind of annihilation reactions, and how to achieve kind of what you might call a 0 point energy device. Nebulous, very, very embryonic stages.
Awesome.
And
awesome.
I like to play with pure Dankin experiments and stuff. Very intuitive thinker. Not much on the maths yet, but I hope to change that.
Brendan, thank you, man. Thank you. And welcome back. Let me go to Richard Bandurek next. Sir?
Hello, yeah, my name is Richard Bandurek, and I'm really just a researcher, just doing some research under National Science Foundation. And I'm just here to listen to see what everybody's working on.
Awesome. Richard, welcome back, sir.
And
okay,
thanks.
now let me go to Jim Marson. And Jim, let me apologize for the confusion. I mixed up my Jims earlier.
Happens all the time, no problem. Yeah, actually, I work as a software developer at the moment, but my true passion is classical physics. I'm an advocate of a classical ether theory called the local ether model, which I believe could completely disprove Einstein's relativity. I'm also extremely interested in the Biefeld-Brown thrusting mechanism. I guess that's enough for now.
Well, thank you, Jim. Okay, and let me go next to Mr. Michael Boyd. Welcome back.
Hey, how's it going?
Pretty good. And you have that patent too, right? Don't you have a patent that's coming out?
I have 4 patents in the United States and 1 patent in India for gravito-magnetic induction. And my recent paper is IEEE Sensors Journal article called Resolving the Extra Dimensions for Gravity. And I'm curious to have a dialogue about space-time. The question is space-time non-linear or is it linear? And a good example, and when we talk about that, we think of space as three-dimensional. Then the question resolves around the question of is time linear or not?
Yeah.
And there was this guy called Gödel. He had this universe where you had what's called closed time-like loops, where you could basically time travel. And it was theoretically possible using Einstein's field equations. So I'm curious about people's thoughts on that. Is space-time linear or nonlinear? And likewise, is time linear or not?
Well, and Michael, that's a great kind of cliffhanger. So let me go on to the next person. But what I'd suggest is I think you just had a PDF that you sent out. You might consider uploading that into chat. PDF files are pretty safe.
Yeah, I can do the preprint, but the IEEE article itself is
that's
copyright, so I can't do that. Right?
Okay. Yeah.
Okay, but I'll do that for sure. No problem. Okay.
Absolutely. Okay, let me go to let me see, V. Sears. Sir?
Hello. Can you hear me?
Yeah, I can. Sorry, my Zoom screen just rearranged, so everyone just flipped all at once. So
Okay. Yeah, my name is Victor Sears. My research is mainly in vortex mechanics and how fractals in nature might be usable to as values for capacitance and inductance. And so the patterns and their densities could be electrodynamics, and it totally links up with the fine structure constant. And so that's what I'm working on presenting when I have my papers down on photos in the presentation, is fractals in nature and some scales, kind of similar to how Nassim Haramein had the proton and black holes connected. Mine works with the hydrogen and the electrons orbit and shows that scale in at least three scales in nature that are accessible to everyday people for experimentation. So it's fractal electrodynamics, I guess. Okay. And I'm interested in the graviflyer and its applications then to this property for lift.
Awesome. Well, welcome, sir. Let me go to Daniel Davis next. Welcome back, Daniel.
Hello, my name's Dan Davis. I'm an independent researcher interested in mainly warp drives, and I've been working most recently on the idea that gravity is an emergent force from Everettian quantum mechanics, and we've been working on developing the new field of relativistic Everettianism, and I guess I'll leave it there.
Awesome. Thank you. And actually, I just got, Daniel, for the Digital Temporal Compendium, I just emailed myself a link, and I should probably drop that into chat too. And that for all of you guys, that is a Google Drive. And so we're not going to post that in public on YouTube, but in chat, Daniel has collected really amazing foundational papers on a lot of warp drive and gravity modification stuff from all over the place. And so that's kind of his repository that he's been working from. Let me go to Mr. Ryan Wood next. Ryan, welcome back.
Well, thank you, Tim. I just wanted to highlight the fact that next Thursday in the middle of the night, I'll be on Coast to Coast AM talking about anti-gravity, and I'm certainly going to mention APEC. And I put my email in the chat. So if people have interesting experiments or you think there's something I should say about their work, I'm happy to, in 2 hours, get plenty of chances to plug a lot of the efforts. The other thing I'd mention is that Tom Vallone just came out with a new report, I believe, the Anti-Gravity Report, a collection of seminal papers for futurists. And at first blush, it looks at times very intense with math, but at times light and fluffy with prose. So it may be worthwhile for people to check it out.
Oh, that's awesome.
Personally, I'm working on asymmetric capacitors and counter-rotating magnetic fields with high electrostatic involvement. So that's what I've been working on from anti-gravity.
Wonderful. Ryan, thank you so much. And you did a presentation recently and you've been talking about doing another one as well. But let me urge everybody. And Ryan, if you have a link to the upcoming Coast show, I think sometimes they announce those in advance, or other links that are helpful, drop those into chat. People can use them. And that's just a great way to, again, help share and collaborate. Let me go to Jeremy Reese next. Jeremy? Jeremy might not be here. I can come back to him. Let me go to Curtis Horn next, a man who needs no introduction. Curtis, welcome back, sir.
Thank you. Thank you, Tim. Yeah, Curtis Horn. So I've been working with Jim Woodward on the Mach effect drive. And as you may know, if you've seen my presentations, I'm basically kind of a low-key physicist that I'm very selective about the projects I work on. And so, I've had my own program for quite a while, thinking about physics, and that's where my interest in this comes in from. Basically, I'm interested in general relativity and getting kind of doing the right thing in physics. I would highly recommend, if anybody wants to do lab work and do an interesting experiment that's like something that's attainable, I would love to see somebody replicate Eric Ryder's work. And the reason I bring that up, and it may not seem directly applicable to propulsion, I would strongly disagree, because us knowing the foundations of the physics we understand and what the limits are to those foundations is very important. So if quantum mechanics is an emergent phenomena or fundamental phenomena, that's kind of the question, right? So Eric has quite a bit of work, and it's something I recently found, and I was glad to see him present. So that's, he has his website and the book. I got the book from Amazon just because it's easy to carry around, but all the information is there. And I think he put it in chat for those of you that want to do an experiment. That would be a really interesting one. And like I said, that really, sort of kind of lets us know where the limits are in terms of the energy and what's fundamental here. So in terms of the Mach principle, really, quantum effects aren't something we deal with directly. Jim's derivation doesn't have any quantum in it, right? And that's one of the things that people bring up as a kind of a detraction. But I don't agree with those detractions. I think that's still an open question, right? That which one is fundamental? They're both theories have their strengths. That being said, we do know that general relativity itself, is not really fully the way it was formed. The symmetries that are there are not fully in the theory. The symmetries that we know are in nature.
Yeah.
So there's some improvement there, of course. And there's the question is which direction we go. And so that's the questions that I'm interested in. And again, I'm working with Jim in the lab, trying to get the Mach effect experiment replicable. One thing I want to mention is that we did get a quote on, actually, I'll put it in, I'm going to be putting in my presentation for later, but we did get a quote for having a bunch of stacks made so we can start actually getting
update us, definitely update us on that later. So
Yeah.
let me if it's okay, let me skip back to Jeremy Reese, who's back now. Jeremy?
Hey, what's up? I'm Jeremy
Hey.
From Boston, and I went to Bridgewater State University on and off. Been doing YouTube since YouTube started, and know a lot of people in the whole sphere. So I'm linked in now with like all these top YouTubers and getting them hit up with all the right questions, which come from this awesome community. and we're just pile driving through to the truth because nothing cuts through disinformation like science and physics and the scientific method. So just you guys are the greatest, and I love this community. Thank you guys for being
Awesome.
here.
Well, Jeremy, thank you. And just like everybody else, let me urge you to drop your email into chat for anybody who wants to reach out. You know, that's the best way. Again, I'm trying to foster like collaboration and communication, and you know, you guys can solve problems working together, right? And that's where it's all at. Let me go to Lulu next.
If anyone has an idea for a show or has anything important they want, feel free to reach out. I'm always looking for people to have on as individual, podcast guests for one-on-one discussions. So feel free to reach out.
Awesome. Thank you. Lulu, welcome back.
Hi, Tim. My name is Lulu or Nawal Sajari. I live in Houston, Texas. I'm a licensed health and life insurance agent. My interests are in space technology, in the sciences of the future, which include time travel and space-time engineering.
Awesome. Welcome back. Let me go to
Thank you,
Tyler
Tim.
next. Sir?
Hey, what's going on? How's everyone doing?
Doing well. Thank you.
I'm really grateful to be here right now because usually when these calls happen, I always have some other obligation and I'm just not able to make it. But I've been following Tim for a very long time. I speak with Jeremy here and there. I love what Jeremy does. Falcon Space. I've been following the UFO subject for about a decade now, and I've just been totally fascinated with the opportunities that it presents in terms of alternative energy and propulsion. I think that fossil fuel combustion rockets are archaic, and I think we have solutions that would, be way more efficient than that. Right now, I'm currently working with Danny Sheehan at the New Paradigm Institute. We are a 501c3 public interest organization that's working on Capitol Hill with legislators to make sure the UAPDA gets passed for the National Defense Authorization Act in 2025. We're working with nearly 40 whistleblowers right now to make sure that they have the adequate protections necessary so they can come forward and they can testify publicly in congressional hearings. And that's just a quick background on what I've been working on. And I really love the work that you all do. I think it's incredibly important. So thanks for having me on the call. I appreciate it.
Absolutely. Well, thank you for coming on with us. Let me go to Zoltan Komar next. Zoltan, could I ask you to turn on your camera and do an introduction?
Hi, and I apologize for everyone. I'm trying to, as I have exchanging notes with Brandon, when I click on start video, it says, please select another video camera in settings. So I have been trying to set it on since I appeared here.
Oh, okay. It's having issues. Yeah.
Just a sec, maybe now. No, it still says, can you help me? When I go to, and I really apologize for everyone, when I go to start video settings, it doesn't even appear there. What is supposed to be the problem?
Yeah, I can't tell you about. Well, Zoltan, welcome, sir. Let me go to Stephen Carmen next. Stephen? Okay, and it looks like nobody is there. That's okay. Okay, and then let me go to GJD next. GJD. Okay, yeah, looks like nobody is there as well.
I'm here. Can you hear me?
There. Yeah. Can I get you to turn your camera on?
I have a problem here. I lost my internet just before the thing came on. I'm trying to do this from a cell phone.
Oh,
and,
okay. Limited
so
bandwidth.
I'm basically just trying to listen to what's going on here. I've got a lot of interest in various space-time engineering metrics I'm studying, and also in some condensed matter physics, specifically with 2D twisted metamaterials and how that may apply towards space-time engineering. So,
okay.
But I'm just here right now to kind of sit around and learn.
Awesome. Well, thank you. Let me go to Jonathan Saunders next. Jonathan?
Hey, making sure we get a hot mic. Is it good?
Yeah, welcome, welcome.
Yeah, it's been a long time from NanoX Solar and J4 Technology Group. Towards femtosecond lasers and Tesla crystals, obviously nanomaterials with sodium phosphate, platinum, neodymium doped glass. We're the specialty experts in creating nanomaterials. So if anybody needs any test sample material, we're happy to help with some of your research projects and custom crystal and coating. Whether it's HR, AR coding, and nanomaterials, please reach out and we can help you with your photonic projects. These are
Awesome.
the things that basically create the gravity waves with the diode pumps, pumping the femtosecond lasers for spinning disk lasers. If you've studied some of the fusion technology from the Germans and the Japanese, we can help with some of the research data for Fermi well bands and being able to use those Hamamatsu sensors to capture the data points. Please reach out for a private message. My name is Jonathan Saunders. Happy to introduce myself.
Jonathan, thank you. Why don't you drop probably the best way to communicate with folks is to drop your email into chat there and they can reach out. And it sounds like you guys are involved with crystals, metamaterials, as well as data analysis. So if you guys have needs there, that might be one resource for you. Let me go to Brad Hammerstrom, and then I think that is everybody. Brad, welcome, sir.
Hello, can you see me? Oh, there I am.
Yeah, welcome back.
Hi, thanks. I'm Brad from Canada. I have nothing to contribute at the moment. I'm just really interested in alt propulsion because I've always thought that anti-gravity was the big necessary step to human advancement. I think it's a step as big as the wheel, bigger than internet, maybe as big as fire. I don't have anything to contribute right now, but if I hang out long enough, maybe I'll figure out how.
Awesome.
I would basically pay to watch you guys. It's super interesting. That's about it.
Well, Brad, thank you. Thank you. And I see a growing, I think that's everybody. So we'll kind of come back and do ad hoc presentations. One thing, again, thank you everybody for joining us today. It's really exciting being able to run through and have everybody introduce themselves. And this was actually Mark Sokol's idea. He's like, we got to grow this community and get people collaborating and interacting more closely. And so Mark, thank you. I see a bunch of links in chat. I'm going to add one more. Maya Stanovic emailed me last night from Ireland with something called ring theory. I cannot make any claims about it, but it was interesting. They were basically talking about magnetic effects inside elementary particles, right? Protons, electrons, neutrons, and how those might change physics and provide at least a new way of visualizing things. So I'm going to drop ring theory in there, but again, we've got a bunch of emails and several links, and it's all exciting stuff. So I guess I should ask who has something to share first. And again, I think that the one that comes to mind was, well, actually, yeah, let me go to Robert first. Robert, go for it, sir.
I conducted magnet drop experiments to determine if inertial mass or gravitational mass was being altered, and that's why magnets might fall faster or slower. Let me pull up my PowerPoint presentation.
Awesome. Yeah, and let me know, you can share. That's super easy. Or if you want to share videos, anything along those lines.
Yeah, I wanted to do a share screen. Um, Not sure exactly how to do this, unfortunately, but
So yeah, Zoom will let you it'll either let you share a window or your entire screen. Right now we're seeing your entire screen. It looks like you've got Slack. It's showing us Slack and it's showing us your Amazon account.
oh, okay, that's the wrong monitor. Shoot. Uh, Sorry about this. Uh, yeah.
Oh, no worries. Here, you know what? Let me do this. I'm gonna do a stop share on
Okay.
that. Okay, and then if you click share again, it should pop open a window that's
Oh,
gonna.
here,
There we go.
you see
Yeah,
it?
perfect.
You can
Runaway
runaway acceleration.
acceleration.
Yep. All right, awesome. Okay, so yeah, runaway. I got a runaway acceleration resulting from inertial mass reduction. What I found was is that when I had magnets with the north, I used two magnets for each of the magnet objects, and I tested four of them along with a control group. And the north-south magnet, where there's the North Pole on top, South Pole on the bottom, and then a North Pole on South Pole on the bottom, it continued to accelerate until it hit the ground. This graph represents T minus 250 milliseconds before impact up to 10 milliseconds before impact. So you can see that there's only two of them. And the NSNS AUD just represents the Arduino that I use that has an accelerometer built in, turned upside down. So that's the result I got. I got it from I did 25 trials per object, and I averaged the results. So for this, I for across the 25 trials, I averaged the 250 millisecond time, and I did that for so on for all the different times. We could skip again past this. Yeah, well, like I'm saying, only one magnet configuration displayed runaway acceleration. It hit the ground at around 11.125 meters per second squared. There was a kind of a strange result with the SN Arduino upside down, which plateaued around 10.15 meters per second, but it didn't really replicate the continuing acceleration effect that was seen with north-south, north-south. And then of course there's three possible explanations for this. Thanks to Mark Sokol, who recommended Byfeld Brown's journal, who talked about perhaps that gravitational mass and inertial mass can have an inverse relationship. It made me think, well, maybe this field was affecting both. But yeah, so of the three explanations, you could have north-south. You could have gravitational mass that's causing it to fall faster. If it's increasing the gravitational mass, you could have a decrease in inertial mass, and that could cause it to fall faster. Or you could have both an increase in gravitational mass and a decrease in inertial mass. And the masses were virtually identical. I weighed them all on an analytical balance. You can see the aluminum bolt, washer, hex nut, they're all relatively the same. The reported weight from the manufacturer, 380 grams. Of course, I was using two. And then, of course, the magnet object total mass, which I weighed on the analytical balance. I used 30 sheets of XPS foam as a barrier between the analytical balance and where I put the magnet to ensure that the magnet was not affecting the analytical balance. I used the magnet pull probe near the bottom just to make sure it wasn't pulling up to that. And if the NSNS magnet object was modifying gravitational mass to increase its free fall acceleration, the north-south object would be the heaviest object weighed by the analytical balance, and it's not. Further research necessary. Does it ever plateau? I only dropped it from about 10 meters up. I was standing on a chair dropping it from the top of my ceiling. Would a more powerful magnet achieve a higher plateau, or just higher rates of acceleration per each snapshot by the accelerometer? I don't know. But I would say equivalence principle violated. So the next steps, I was going to, like I said, drop it from greater heights. I'm going to add fins to the plastic shell body so it will be more likely to drop vertically and not tumble or rotate and stuff like that. And I'm also going to use N52 magnets. They they didn't have them with holes in them, but considering the main effect seems to be with the, north-south magnet, I'm just going to use, I don't need a bolt through them to hold them together for that. So I was going to do N52 magnets in addition to the N41, N42s I already used. So my work is available at robertfrancis.com, robertfrancisjr.com. And last thing, ArcSiv requires that a user be endorsed before submitting their first paper to a category. The endorser would need to be published in physics, the applied physics section. If you can help me out with that, reach out to me at robertfrancisjr.com.
Awesome. Robert, thank you. So
You're welcome.
let me remove the spotlight there, and I'll stop the sharing on it. So I think that's really interesting. That's an experiment that I'd love to see more people replicate. And and then one of the things that came to my mind, and I'm not sure what the physical apparatus looks like, but if you're doing like a chamber to drop these, maybe if you had like a plastic, like a almost like they put stockings in, right? Some kind of a plastic ball, and that way you could eliminate changes in airflow from different configurations,
Yeah, that was the problem. I didn't know exactly how. I, initially I was dropping them from outside because it was going to be from a higher distance, but then I was afraid about wind effect and stuff like that, so I decided to drop it from the inside, and I made sure I had the AC off and stuff like that. But yeah, I definitely want to do higher distances. Next, I was thinking outside my dad's house's second story window, which overlooks the basement, and see if they plateau there.
Yeah, that'd be really interesting. Well, definitely keep us updated on it.
All right, awesome. All right,
Awesome.
thank you very much for having me on here.
Oh, absolutely. Let me go to Phil Bouchard next. Phil has an update. So, Phil, I think you're doing an update on the gallium, right?
Yes, exactly. And a stack of other important, very important experiments that are not related to anti-gravity, but they're kind of energetic, kind of related to energy. Um, but first, I did introduce myself very quickly, but I wanted to say that I studied mathematics, computer science at the University of Sherbrooke, and I do have a freshman background in physics. So, so I understand the objective point of view of pretty much everything. So let me share my screen now.
Yeah, go for it.
Uh, okay, presenting for Knox. Here. All right.
There we go.
So
And
these,
it looks like there's something over part of it.
uh,
Oh, maybe it's your Zoom. Yeah, it's your Zoom window, I think, or something. I don't know. But
yeah,
yeah,
I think it's the control window of Zoom, but it just says Phil Bouchard anomalies September 2024. I've got 4 experiments I would like to share. Starting with the most important ones. First being the electrolysis. Second, anti-gravity. The third, the Cavendish experiment. And the last one, I'm trying to measure the frequency of a permanent magnet, but I don't think that's possible because it's too low. So first, the electrolysis. I did an experiment recently on the electrolysis, and I wanted to test a way to improve the generation of hydrogen, because the problem with electrolysis right now is that it's 3 times it costs, the input of energy required to generate hydrogen, which that we can use to generate a combustion. You need 3 times more energy than the output energy, so it's 3 times less effective. But if you increase the temperature of water, by 13 degrees, then you're gonna generate 150% more hydrogen. So if you extrapolate to boiling point of water, then you're gonna generate 900% more hydrogen than the room temperature. So it's very important because it can easily replace fossil fuels, electric vehicles and all that. And what led me to think about this experiment is based on my theory that I'm not gonna talk about right now, but I'm just gonna resume very quickly that the atomic forces can be dilated by the linear charge density or the capacitance or the dielectrics of the material. And the only way to do that, it's pretty easy to increase it. You just add a capacitor, but to lower it, somebody, I'm not going to name names, but somebody told me, give me a hint that by changing the temperature, you're going to be able to lower the linear charge density. So that's exactly what I did. I cooled up the water, I heated it up, and I saw the big difference. So um, I'm gonna ideally we could just go to the gas station and order hot water, to to fuel your engines. That would be pretty effective. Or you use the radiators, the radiators, hot water. You use electrolysis on it. It creates water as a resulting combustion. It can be used like a cycle in a cyclic way. So that's the first experiment. Second one is the anti-gravity one. It was performed in a professional laboratory. I do not have the video and the exact detail of the resistance and the temperature and all that because I need to pay for the bill, but I do have the big picture. And on the left, you can see the gallium vortex. I'm using two neodymium magnets of 1.4 Tesla each with 1.5 kilogram of gallium. And the dimension of the apparatus is around 11 the outer radius is 11 centimeters and the inner radius is around 5 centimeters or 6. So that gives an idea. And the apparatus on the left was stacked up on the support on the right, where we see three balances because there are three balances because we want to measure the precision of the experiment at the same time. So with that said, the results of that experiment is that with 153 amps of current, there was a weight shift of 2.6 grams. So around, like again, there was 1.5 kilogram of gallium, and we were able to see a shift of 2.6 gram of on the balances. The total of the three balances added up gives 2.6 gram. But it's right on the edge of the uncertainty of the measurement measurement the balances. So it'll have to be redone with a greater current, but at the same time, I was expecting something like that because it's an extrapolation of what I already done at home that gives something like that. So it can be a good starting point with to Mars Sokol. I'm giving numbers here because it can be a good starting point to Mars Sokol, and then is an improved version of this experiment. And so that's the integrity and so that's about it. And here are the maths. Basically, I'm not going to go through the maths too much, but for a distance of 0 meters, you have an acceleration of 0.02 meters per second. And that gives a mass difference of 2.6 kilogram, which is 2.6 gram. Sorry, 0.0025 kilogram or 2.6 gram, which gives an approximation of 1 times 10 to the minus 12 meters per kilogram for the gravitomagnetic permeability. This is the ultimate constant hidden behind everything here that I kind of I'm solving using the experiment. So I was 600 times off the what I thought it was. So yeah, maybe it still needs to be narrowed down, but that gives an idea. That's a relative gravitomagnetic permeability. That's not the absolute one. There's a big difference between the two. The absolute one is minus 27. The exponent is minus 27. So yeah, that's the hidden variable behind all this. And here's the Kevin. Sorry for the flash. It's flashing here. Sorry about that. I redone the Cavendish experiment of the Fell Forward Research Lab or Wayne Ohala. He had the great idea of doing the Cavendish experiment. I redone it using LED lights. So LED lights, they don't heat up that much, so it's not going to create a air pressure or anything like that, a differential of air pressure. So we see the rod is being attracted by the light, and the idea here is that the energy potential creates. That's what gravity is. That's the same thing. We call it gravitoelectric, gravitomagnetic, electric or magnetic or electromagnetic is the same thing. You have an energy potential, and it has the same effect. It creates a force or an acceleration. So that's what I'm trying to promote here a little bit. But this experiment will have to be redone in vacuum to be 100% certain that there's no air heating up or anything like that. So if somebody has a vacuum box, a vacuum room that he can replicate this experiment, that would be a great experiment to replicate for the third time. So and I'm trying. My last experiment is, well, not my last, but another experiment is I'm trying to measure the permanent magnet's frequency, but that's impossible with the equipment I got recently because I cannot go lower than 24 megahertz. So I anticipate the magnet's frequency to be 0.001 hertz, which is lower than a half wave. So why am I thinking that? It's because if we take the standard energy density equations, then you must have a frequency and a particle density. So you cannot have a null frequency or a null particle frequency, which is U in that case. So you need to have a frequency or n particle density to have a energy density. Call it a magnetic field or electric field is the same thing. So you need both of them, and also according to my basic calculation, a Tesla is some sort of constant times a frequency, and that constant is the number of kilograms per coulomb, or joules per coulomb, which is around 1121 joules per coulomb. which is based on the square root of the magnetic permeability divided by the gravitomagnetic permeability. So yeah, that's my presentation here. I'm pretty much I'm done presenting, so I don't want to go too much in the theory, but that's the result of the 4 experiments. I also did another one, which is the a magnet with an interferometer, but it's so sensitive. I need to replicate that one for a third time. So yeah, thanks for your time, and thanks again, Tim, for giving me the opportunity to share all that. You're muted.
Sorry about that. Phil, thank you. So this probably makes this a good time to at least broach this topic. And Mark Sokol wanted me to bring this up. So one of the things that I have been noticing, we have several channels in WhatsApp, and those have worked fairly well. But my worry has been WhatsApp is becoming more and more of a target for hackers. And so I've wondered about moving those over to Signal. And the reason I've done it is what I've seen is with the people that I talk with, more and more of them have been going to Signal over the last year, especially. I think we've all had Signal for a long time, but it seems like we're actually using it more now. And with WhatsApp, one of the things that I noticed was Facebook can do password resets. They do their two-factor authentication through WhatsApp. I think that is why it is being targeted by hackers, because if they get that, they can use, or they can at least attempt to use your Facebook to hack that. So I don't know the details of it, but I wanted to see what your guys' thoughts were on potentially moving the APEC 24/7, maybe consolidating it down to a single channel, and potentially moving that from WhatsApp to Signal. Another thing that we talked about was maybe moving that over to Reddit, which may be good, may be bad. We already have a Reddit channel that nobody uses, so I don't know. Curtis, go for it.
Curtis is not talking about that. So if you want to have an open,
okay, yeah. So,
there's a lot of issues with having a single channel. The main issue that we're having right now is, let's say somebody comes on and says, "Oh, I'm working on this great thing. Here's pictures of this amazing thing that I just worked 6 months on." Then anyone can then type into chat and have that thing buried in 2 minutes. This is a problem even with multiple channels. It will only get worse if you consolidate it to one chat bot. Signal, a lot less people have Signal versus WhatsApp, which is why we went to WhatsApp in the first place. But I don't really use the WhatsApp group that much. I know Phil does, which is why it's great that we have you here, Phil. What are your thoughts on this? Should we try to change anything up? I know we had a problem with bots infiltrating it this past week, and I put on some safeguards for that.
I assume Discord's not secure enough.
The problem with
Discord, I mean, you're running into the same problem. Like, not everyone has it, and then I
mean, not everyone has Signal. I love Signal personally.
There are no mods right now in the Discord. There are no mods, and I meant to mention this to you guys. There's like a actual bot, like ridiculous troll in there named Gen Z Boston and Mini, and just throwing this out there. Somebody with mod powers needs to take care of that.
If you want to be a mod for the Discord group, I mean, we have I created all of those. Okay, yeah, shoot me an email and I'll log in and
we'll do.
I can testify to Brendan's. He's pretty good at moderating on Discord, so he should.
Well, and Daniel, you as well. If you want to use Discord, a lot of this kind of came out of like what people are kind of. It's one of those things where it's like, what are you comfortable using, right? And so we created a bunch of these all at once. Like I created a Reddit channel that doesn't really get used, and then we created a Discord group, and we have a few folks that post on that, but the majority not. And then most people kind of went to WhatsApp, and that seems like it's kind of worked for the most part. And I really appreciate Phil taking like a leadership role in moderating that. The only challenge there was it seems like, and this has just been the last couple of weeks, it's just been like bam, 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 bam in terms of like potential hacks, right? And that's made me start to. I always feel kind of nervous and cringy when stuff like that happens. So.
Yeah, it kind of slow down by demanding, requiring, uh, accepting the members or something like that Mark added. So it kind of slow down. But the problem with WhatsApp, what I don't like is new members, they cannot read messages in the past. So they're only able to read message posted from the day they log in.
Yeah, that is a big downside. Signal doesn't fix that problem. On the other hand, there's other systems such as somebody recommended Wire. I'm not really sure what that is.
I don't know what that is.
Reddit has its upvote thing, which is great. The problem with Reddit, though, it's not conducive to a continuous conversation. Correct me if I'm not that big of a Reddit user, but it's sort of like, which way is the best way to bake sourdough bread, and then you have a million answers. The best way gets upvoted, so it's a question answer thing. It's not really a conversation. I'm running into this problem. Oh, you try it that way, or with a continuous growth of an experiment, or have an actual conversation with somebody at 3 a.m. It's not really conducive to that.
So in terms of Discord and Telegram is the other one. I looked at doing both of these at once. Discord, I started the feedback that I had, right? I'm not making a judgment, was especially the emoji in it, which I guess you can turn off. People didn't like it. They felt like it was for little kids, right? Even though it's not, but they didn't feel like it was mature enough for our.
It's very customizable.
Yeah. And so that was Discord. And then with Telegram, I've used that in the past, right? Like during, but that is primarily for crypto stuff. And what I've heard is like the founder of that just got arrested, I guess, for their lack of security. So Telegram might be the wrong direction.
Yeah.
I think it was for the effectiveness of his security, and he wouldn't let the government have access to their algorithms. So that it's kind of like an advertising point, in my opinion.
What I like about Telegram is highly searchable, right? Because basically it's just kind of like a web page that you're adding to. But then maybe it's a little bit too open. I think that was kind of the issue.
That leads really well into the question that I was going to ask. And if you're not comfortable divulging this information publicly while the stream's going, we can talk about it after. But how does the invitation thing go for these groups? Can you just sign up for it on APEC's website and get an invitation, or are you only giving it out to people that you've actually interacted with on video?
Well, so for WhatsApp, the way for all of these, I put links to the groups and people can request to join all of them. And then one of the big ones that's been around for years was the Facebook American Anti-Gravity group, right? The discussion group became the Facebook Alt Propulsion group. And so that's got 4,000 something people in it, right? And that one is literally just you get on Facebook and you join, and we've got 4 or 5 people that are doing moderation there. And then WhatsApp seems like that is the other big one, right? And thankfully, Phil is kind of he's doing a leadership role in moderating. And then with Discord, it's been there for a while. Periodically I log in, but it's got kind of a small group of people that post, but it hasn't caught on, or at least not yet, so.
Well, Curtis mentioned Slack. That's for like a more tight-knit community of actual builders, and I kind of like that idea too. If we could have a Slack group with everyone that's actually building something, and that would be invite only.
So the only concern that I have about Slack is if you have a paid company thing, which we have too many people for that, right? If you have a paid company thing, it's a really good tool. It's comparable to like Signal, but it stores it in the web, the whole 9 yards. If you use the free version, if I remember correctly, it only stores like 20 conversations, and it's like it running deletes them unless you pay money. So
Can go back to tap a talk also, but you just need to refresh the page all the time. That's the only annoying thing about tap a talk.
yeah, yeah, and so the Tappa Talk, if you guys haven't seen on the Alt Propulsion site, that is our what do they call it? That's our forum, right? Our BBS. And for me, that's a little bit more familiar because I used to, like when I got into this, it was Yahoo Groups back in the day, right? And everybody was doing Yahoo Groups, and that was structured more like a traditional, discussion forum. So, and Tappa Talk has a few folks that use it as well. Like I know, again, Phil uses it. Todd Desiato, he feels more comfortable with it. So, we've got a bunch of different forums there, but and maybe that's the issue in today's environment. Things are really scattered, so maybe there is no perfect answer.
Well, I think it seems that's probably right on the money where there's no perfect answer because it seems like we're running into some people want more security versus, chatability, and some people want more open chatability versus, so I think we got to figure out what people want.
Yeah, yeah. Well, and then there are the email chains, right? Which is what and one of the reasons I don't use the online tools that much myself is because I get CC'd on all these emails. So it's like, if I make it out of my inbox, that I feel like that's an achievement, So
Slack, by the way, is $8.75 a month. That's $8.75 a month. Not
per user, right?
No, it says small teams who want better. It doesn't say anything about limit of number of users. No.
I would say I would go like my professional opinion as a technologist is all of the above is fine as long as you have moderation in each location. Everybody's going to fall where they may.
Okay, so maybe
I think another thing that we might want to try, and this is something that I've already done in one chat group for WhatsApp, is only admins can post into a group, like the announcements page on WhatsApp. I just made sure only admins can post in there, and the only thing I post is like the announcements that are coming out via email are also coming out via WhatsApp. That's so keeping things simple and limiting the number of people that can add to certain groups might help with just the sheer overload. Like if I were to go and post something that's really cool that everyone wants to see, and then have 20 people post another 50 messages afterward and get it buried within half an hour, it feels sort of like a waste because you can't see it. Nobody sees it. So having some groups that are admin only for posting would I think would help. But yeah, definitely do not want to have one group. We started with one group. There was too much crosstalk. There's too many cross conversations.
Well, so maybe it's just about. So maybe I should just ask anybody. And again, please email. Right? You could use like the tim@altpropulsion.com. That'll work. Or Mark has dropped his in there as well. If you want to be a moderator on one of these channels, let me know, and we'll get you set up as a moderator. And that helps, right? And then we'll all just kind of suffer through email lists as we go, which are those, as you all know, those are the mainstay, right? More emails than anyone wants or needs. So.
Zoltan Komar says that there was a manned mission to Venus.
I'll tell you, I just saw that video, the video that just came out of that spacewalk, and the part that got me was the flight suits. Those are really cool. Was it the New Dragon
Sorry,
mission?
I was gonna mention that, but really, I'm sorry, Tim. I'm really doing my best to fix my video, but unfortunately, it will not be happen now. So when I couldn't fix it, you took away my word. But I was gonna say some words about this man missions. Actually, I tried to have some documents that I can share by next time, but the U.S. Navy is preparing a crew of 4 manned mission to Venus by the end of the this decade, but it will be like that, like a 2.0 mission, because the first one happened in the early 60s. It was a crew of three then. It was piloted by a gentleman named Captain Williamson. I know because I met this gentleman several times in the Clearwater, Florida area. So yeah, just two remarks to mark that. So what about this upcoming U.S. Navy mission that they are preparing to conduct like within 5-6 years? I hope to share some documents next time.
Okay. Yeah, we could use GitHub also for a repository to store all the documents. Otherwise, if you post that on WhatsApp, it's gonna get lost after a few months. So we could use the combinations of things.
Rick asked about, let me see, I'm just going through here. Let me see. Jim mentioned Google Groups is like Yahoo Groups. Yes, it is. I've used Google Groups. I like it. It's a little bit harder to navigate. It's interesting too that Yahoo Groups, they just closed that down actually 2 years ago. I think the problem is that we're used to a little bit easier to use stuff now. And I think that's why Tapatalk is having trouble too. The traditional BBS, that traditional web forum, I think it just feels a little dated. And then Rick mentioned Microsoft Teams. He said it comes with every Windows PC. My understanding was to really use Teams, you had to subscribe to it, and that would kind of be like, I think that would be like Slack, but I'll have to do some more research there. I mean, yeah. So I think for the time being, again, guys, just email me. The Tim at altpropulsion.com if you want to be a moderator on one of these. Jim's saying the IRC is still around. It is. IRC will always be around. Internet Relay Chat. I think we could do that.
No school like the old school.
That's right. Yeah, IRC. We command line chat like the old days.
Those servers don't exist anymore, the NTTP server.
Oh, Curtis is asking. Yeah, Curtis, do you want to do an update on Mega Drive stuff? Yeah, go for it, sir.
Let me share my screen. All right.
Awesome. Looks great.
Okay. So I did give a short update at the APEC, but I'll kind of cover everything. So we've been working on the bearing design, and we have placed bearings further apart somewhat. It's kind of like a hybrid installation. I'll show a picture of that. And in terms of sourcing materials, we did get a quote recently for piezo stacks of different sizes and types. And so that is basically four different types of builds, 10 of each. So that number kind of adds up. And so that's something that we need to discuss and, going further here about the funding. But also in terms of testing other bearings, like I mentioned, in terms of the 2-to-1 rule earlier, we do have a hybrid design where we're testing these flange/sleeve bearings and a bearing that has the ability it's a ball that has the ability to move. And also, we are looking at figuring out how to get better data as well. So in terms of our testing, we have not, we're still in the vacuum chamber. We're still doing that. We are trying to get a pump shipped in. So that's in the works. But we're still able to get like between 1 and 2 times 10 to the -4 torr. So we're still able to get a good vacuum, but we're hoping that the new pump helps us once it gets in here. And we haven't done any further testing on that. So in terms of the funding, basically we are looking at trying to do some crowdfunding. So we're going to be having those discussions coming up. It was something one of our team members Michelle, she ended up in the hospital. And anyway, fortunately, she's on the road to recovery, which we're thankful for. It could be a relatively serious issue. So we're all hoping for the best for her. But we would like to get it out there, put funding for us to continue to fund her lab work, because she's, of course, she's going to take a financial hit due to that. So we got to figure this funding stuff out. One thing I was looking at, and in terms of a model, is the stuff Eric Lerner's doing for his fusion research. I know he did a crowdsourcing, which was a kind of like an official thing where people get like shares in something, a company or something like that. So we're exploring those things and trying to figure out, what's appropriate for us at this time in terms of the stage of research we are. And in addition, we are looking at the SBIR as a NSF SBIR as a serious next step. So that's in the works. So this is a picture of the device that is still in the chamber. As you can see on the left, it has the aluminum cap has a different bearing than you can see on the right. So that you see this larger bearing here in terms of the outer diameter. So it's basically it's a ball that can cantilever, and it actually has extra degrees of freedom, right? So as opposed to the sleeve bearing. So it's supposed to allow for more vibration and less impact on and less binding and stick slip and that kind of thing. So unfortunately, we were trying to get all the bearings of those type, but we had some fitment issues. So actually, Jim built this hybrid device, and you can see in the bottom, the middle, there the bearings in the bottom weren't. He didn't put them out here on the outside where I expected. He actually said, "Hey, no, I'm going to put him in the center because that is sort of a balance point." So this is quite something different that I would have thought of doing, but he was able to get that to fit, and this is actually what's in the chamber and has been working. So I want to reiterate our initial work with these the bearing that's on the left here. These are the ones that Jim calls the big ears, because they actually require us to have larger supports. And so this was one of the initial runs we had back in early August 1st. You can see the date there, where we actually had a pretty big signal, and we were able to get that run an average of 700 millimeters is what we calculated on average. Now, what I want to do next is go over and show you the videos of those runs and recap those. So that run that was shown there was this August 1st run. And I'll skip ahead like I did before, because it's pretty stable until it gets to near the resonance. And you'll be able to see this push to the right, and it relaxes there. So that was that graph I showed earlier. This was the run for that. And what ended up happening is that between August 1st and basically it took us a whole month, because we tried to replicate it, but there were issues with the bearings falling out. Jim ended up using a little bit of Loctite and getting the bearings so that they would stay in place. And we had other issues in terms of fitment. And finally, at the end of August, we were able to replicate it again and do that run again. And so here is another run, and you can see initially it's not as smooth as before. It wiggles around a little bit more than did previously, but we get the similar type of push. And you can see this went off scale, but the scale is 2.5 volts here. The previous one was 5, so it's a very similar run in terms of that. And of course, at this point, all these bearings are put in place with some Loctite, so they're not falling out like they did before. Before on the next day, one of them ended up popping out. So that's what took us time to get that working again. So that's this is the big ears device. And again, the progress we've made is what we're testing is actually getting those bearings further apart from each other, so that the 2-to-1 rule, so that we don't get issues with binding. And so this is a couple runs with the device I showed in the picture, where there's bearings in the center and off on either end on the outer parts of the device. And yeah, this is already skipped ahead. I'll skip ahead a little bit more. So this happens to have a frequency where it actually reacts at a different range than the other device did. So because it's mechanically different, we get resonant at different places. And you can see that there's quite a this is at 5 volts, so it's double the scale that was shown earlier. And you can see that there's as the sweep is going through, this is a 40-second sweep, you can see there's a point there where the resonance is pretty evident. And so what I want to do is go to run number 5, which narrows in between 24 and 26, I think 26 and a half kilohertz, 24.5 and 26 and a half kilohertz. And you can see that this repeatedly does a push as it sweeps through that narrow range. So you can see that it starts kicking in and it kind of pushes to the right. And so that is the kind of behavior we would want from an impulse drive, where we're like consistently able to get the same push. Now we still need to run these through to tracker to confirm that it's not pure stick slip. So anyway, so that's the lab update. I won't go into the theory today, the theory talk today. I think we can do that another time.
Awesome. Okay, well, Curtis, thank you, man. Here, I'll remove Spotlight real quick. And Brendan, I got your email about moderating, and I'm just going to mark as unread so I can respond a little bit later. And yeah, I mean, again, anybody who wants to moderate, it's just tim@altpropulsion.com. Let me know, and you know, we'll kind of roll from there. We have a lot of stuff going on this fall, so things are crazy. And then, oh, the other thing was Drew from sunny Florida has an extra vacuum pump and 2 diffusion pumps that are available for folks who have I put a good size vacuum chamber, because like Curtis, yours is kind of an example. The system you have is slightly smaller than Drew's, but what I've noticed is when you build a vacuum chamber, it kind of takes over your working space, right? It's just like, it's like the Borg, you know, your room just progressively becomes more and more vacuum chamber equipment. So, you know, this is not like an at-home thing. You kind of have to have a dedicated space. And the other part is these things are freaking heavy. The pumps are like 200 something pounds. And that's the small one. That's just the roughing pump, right? And then the chamber is hundreds of pounds more. And so, you know, you don't want one of these in an apartment. It needs to be in a space that won't change for years. But so yeah, I mean, that's some of the stuff that I kind of had. It's exciting. Let me see. And then Eric Ryder, definitely email me and we'll get you scheduled for, and in fact, I'll make a note there. Okay. Okay, so who wants to go next? Again, it's Alt-Y on Windows or Option-Y on Mac. Oh, Al Baur. Go for it, sir. And I will spotlight you for everyone. You had a couple of videos, right, on new experiments?
Yes. I want to upload the video, if that's okay with you.
Yeah, I think so. In Zoom, you can upload it. You can also do a share screen and play it right from your computer.
Okay.
What you would
How
want
I
to do
that?
is So you would want to get the video up in a window, right? If it's on YouTube, you would want to have YouTube up, or you'd want to double click on it and get that window up. And once it's up, then you click the share screen button, and Zoom is going to give you options.
Okay. Share. Okay. Now. Share.
Yeah.
Okay. Now, what I need to do now to drop it in?
So it's sharing your entire screen. So you might just try double clicking on it.
Double click on what? On the file?
Yeah, on the file. Yep, there we. Oh, okay. Yeah, try double clicking on the video file.
Okay. All right.
Okay. Yeah. Okay, so the problem is it's showing the Finder window. It's showing your file manager window that those are in.
Wait.
But we can see your screen. So if you actually just play one of those videos and maximize it.
Okay.
Yeah.
Let's see if this works. No? Okay. Wait.
Okay, so yep, so
wait, maybe for now, no, also not. Yeah.
So you've got those video icons. Well, you could try highlighting one and clicking play.
Okay. Now, double click. Okay.
There we go. There we go. Okay. So it looks like it is coming up. There we go.
Okay, what we see here, it's Einstein and Newton levitating in a field.
That is the cutest thing I've seen all week.
I am amazed. I'm amazed by the fact that you're able. So there are no wires, right?
Here we have a Delta flyer. So I try to make different shapes. Okay, now I have a question for the whole team, if you allow me. Where can I see the team? I want to see the whole team.
Oh, okay. Why don't I do this? So let me stop sharing. I'll stop your screen share.
Okay, I have a question for the whole team.
I'm going to remove Spotlight. And then if you go in the very right-hand corner, you go to gallery mode. Yeah, you should be able to see everybody in gallery mode.
Tim, you didn't. All you have to do is go to the corner.
My question is this. I sent information of electrostatic levitation with propulsion to 14 professors over the whole world. The best answer that I received was it is a fake. Okay, the last time I was here, I explained how it works. And now I ask all the people that see this or saw this or hear me, do you believe that this is fake or is this real? So if it's fake, please show me your hand. Who thinks that it's real? Show me your hand. Okay, thank you. So you are more intelligent than 14 professors over the world. Okay, thank you. This is, I have another video where you can see what happens if I make stop start. I don't know if this is interesting, Tim. You hear me, Tim?
Yeah, sorry about that. I was distracted here for a second.
I have another video where I can show what happens when I stop the voltage and I restart. Is this okay? So I have to see how I fix this now.
So you want to share your screen again? Sorry, I'm trying to message Eric, but I did. In fact, maybe I should put this out there for you guys. What I had, this is just me, right? It could just be random luck, but I had 2 colleagues that were hacked in the last week, and I had someone make an attempt on my WhatsApp password. And then I talked to a friend, and she said that somebody had done the same thing. They were trying to phish her WhatsApp password. This is all like in the last week and a half. And so for me, that was kind of like, you know what? I think that this is related to election stuff. What I heard was the last 2 election cycles, you had foreign nationals trying to hack into social accounts so that they can basically try and manipulate opinions with fake news articles and stuff like that. And supposedly there are bot farms in different places in the world where people do this. So I thought, you know what? It's time to update my passwords. So I'm going to put this out there before we go to Al's thing. I want to put this out there to you guys. If you haven't updated your passwords in a while, this would probably be a good time to do it. The other thing, let me recommend this to everybody, is at least turn on 2-factor authentication. And that's where it texts your cell phone, right? And you can also use it on your phone. You can also use an authenticator app. There are a couple of ways that you can do that. And some websites, especially if you have a device that supports fingerprints, they have what they call a passkey. And I've heard mixed reviews about that. Some people say you don't want to share biometrics with big data, big tech companies, but some kind of 2-factor thing, and update those passwords. And that will just save us all, right? Because if you lose those accounts, for instance, my dad had his hacked. He wasn't able to get it back with Facebook. So he had to start a new account. And that is just, it's frustrating.
The other thing is use the Google Authenticator. Microsoft's overwrites your information for an account instead of appending to it. So you can get locked out by trying to do the right thing. So use the Google Authenticator instead.
Thank you, Henry. Yeah, I mean, that's my public service announcement for the week, is just, heads up, it's out there. Okay, well, Al, sorry about that. Do you want to try and share your screen again?
Yes.
Okay, so just, again, it's that green button down at the bottom, share screen.
Green button, okay.
And then it'll pop open a window and ask you what you want to share. You can share the entire screen.
Okay, what you see here is start, stop.
Well, it's not sharing yet, sir. It is.
No?
No, not yet.
Okay, wait.
It'll ask you to select a window and then confirm to share it, I think.
Share. Share. Okay.
There we go. Okay, no. Perfect.
You see my window?
Yeah, summary of APEC 2 movies, start, stop. And it shows the 15 kilohertz oscillator.
Okay.
Yep.
Now, what we see here is a levitator, and it's start and stop is with the remote. And you can see the behavior when I stopped it and when I started.
Now, if I understand correctly, this is ion wind, right? The major breakthrough is the level of control that you have is beyond anything I've seen. But the mechanism itself is very well known, right?
You see here, when it's going to the side, it's able to return to its position. So it's self-adjusting. Okay. I have another video, if you like.
Yeah, go for it.
Okay. You can see it?
Yes.
Yes?
Yes. No.
I don't see it.
Looks like a
Okay,
racetrack.
You're broadcasting.
Yeah.
Okay. This where you see multi levitators. Um, okay, that's all.
Yeah, you have a lot of different devices there.
Okay, thank you, Tim.
Oh, absolutely. Thank you, Al. Yeah, and again, Mark is happy to help you translate. He is one of the few people that I know who speaks and writes Hebrew. So if you have stuff like that, he's more than happy to help. Okay, and let me see. There we go. Stop sharing. Okay. Awesome. Well, Al, thank you again. And let me see, who else has something that they want to share?
I guess I could give a little bit of news on some cosmology stuff that's probably I know a lot of people think cosmology is not relevant to our work, but I can make a connection for you guys. Um, if that's okay, yeah.
Yeah, go for it.
Okay. So how do I want to start this? Looking at the a lot of the new data that's been coming in from James Webb Space Telescope and baryonic acoustallation, or not just at JWST, a lot of different things within the last 6 months has been making the Hubble tension get worse and worse. The Hubble tension being the discrepancy between observations that we actually make with the telescopes here and what we expect that to be based on our models. And where the difference is growing to a point where it's starting to become very hard to deny that there might be some new physics at play at background, at least on the cosmological scales. So what are they finding? They're finding that the cosmological constant might actually not be a constant. It's actually probably time variable. And so that has a lot of implications when you keep following the math down the road of it that would confirm not it doesn't confirm, it might confirm uh or it might lend itself to confirming. I'm getting hung up on terminology, I'm sorry. Some of the stuff that we're looking at. So if the cosmological constant, the dark energy, the 0 point energy of the universe, which is what some people thinks that this comes from, if it's not a constant, well, that means the epsilon mu values of the vacuum might not be a constant, which would lead itself to the idea of vacuum polarization, vacuum bifringence, that stuff, which, and if familiar with these terms, and all of a sudden we start getting into the things where, like showing your energy densities might actually be, we could probably get weird like global plasma states. I'm sorry, my dog is barking. What do you want, buddy? Is she eating your food? I'm so sorry, she's eating your food. But yeah, no, anyway, so we're getting some new preliminary results, and it's only at about 3.9 sigma currently. We need to get up to 5 sigma in cosmology for it to be considered a new discovery. But if this is the case, then it's probably very, very helpful to us in the sense that we should be pursuing some of these like vacuum bifringence theories more than we have been. I guess I'll leave that at there for the moment. Does that make sense?
So does that mean the Big Bang Theory is dead?
Mm, I would say almost maybe the Big Bang might be an approximate value from a certain coordinate reference frame. Um, in terms of like down the road implications of what this might mean. Like so like if dark energy is decaying, what does it decay to? Does it decay to zero? What happens when it decays to zero? Does that mean that there's a boundary at future infinity, which might lend itself to DSCFT instead of ADSCFT? So I'm like, there's a bunch of technical things that might be starting to come in from this. And so I wouldn't say that the Big Bang is doomed, but we might get some more context in which to interpret it.
But this is very funny. Like you started with some substance that is just basically microns in radius, and it grows into this current universe, and the epsilon mu stayed the same. Show me substance that can do that. You can stretch it that much, and its properties stay the same.
Yeah,
That's
and that's kind of what observations are showing is that the properties might not be the same. They're probably not the same. So the cosmological constant is not a constant, it's a variable. At least that's what preliminary results are showing.
Well, I thought that the James Webb Telescope found normal sized galaxies very close to the supposed Big Bang, which essentially means that while the universe is growing, the stuff in it is remaining the same size, isn't it?
So I can share with you some of the papers that these are based on. Here I'll have to find the links and I can share you the archive posts. Um, and then you guys can go and read these all for yourselves. Let's see. I need to find the names of the actual papers so I don't recommend the wrong ones. Oh, one of the other consequences of this is that black holes might be dark energy objects. And if that's the case, then how black holes grow is cosmologically coupled to the event horizon, meaning that there's are going to be some supermassive black holes early in the universe that do have a higher mass than at least our old cosmological models would indicate. And so then that might, if you have something that has a higher amount of gravity than you might expect, then it might cause galaxy formation earlier than we would expect. Have a good day at work. Let's see, dark energy black holes, DES supernova. So the Dark Energy Survey, if you guys are familiar with that, the Dark Energy Survey supernova program is one of the papers that just came out in June of 2024. So, like I said, these are pretty recent things. Let's see, and then the other one is
Hey, babe, I'm going to comment on something. So just so you know, what happened?
Oh, well, Curtis. Okay, sorry, Curtis, do you have something or?
Oh, sorry. I thought it was
okay.
No, I'm waiting to comment on what was just brought up.
Yeah, okay.
Sorry, I'm going to mute myself.
Go ahead.
Oh, sure. Okay. So my take on this is I think we have enough problems in physics than to make an assumption of a measurement. Basically, we do know that as things go further, there's a redshift. But I think and experimentally, I mean, that observationally, we see that, right? But then making the jump to the nth degree where we're, getting a singular, just like conceptually taking that leap, that is, I think needs stronger, experimental basis for, for us making that leap. And by the way, so in terms of the redshift, I mean, there's more than two, but there's two main ways of getting redshift, right? One is having the light source moving away from you, physically moving, like a relative velocity. And one is a gravitational potential difference, right? Just when you're thinking of potential. Now, if there's a thought experiment that I brought up before, and some of you guys might be familiar with it, but I used to bring up a thought experiment, and it was sort of a test when I would talk to other physicists to, figure out if they really knew relativity and knew, the intricacies of these things. And the thought experiment is this: like, take a massive body, right? We all know that if you take a massive body, like a neutron star, what have you, and you're at the surface, you shine a light upward, there's going to be a redshift, right? You're I don't know, 1,000 miles away, you see that light, it's redshifted, right? Now take that same body, let's say you somehow you're able to tunnel to the center of that neutron star, and you have that same flashlight. You're down there now, and you're shining the light, and you're at the surface. Will there be a redshift? And I get various answers, right? Some people say no, there's not. Their first instinct is no, there's not going to be a redshift because there's no change of potential until you leave that body. But if you look at general relativity and you take the interior, there's actually, so for a massive body, there's a Schwarzschild solution. For a symmetric body that's not non-rotating. For a rotating body, there's a Kerr metric, which has a solution for a rotating body. So if you just take the Schwarzschild solution, let's say a static body, and you take the interior solutions, there are interior solutions. It doesn't just end at the exterior, right? And the body could be massive, but not massive enough to cause the curvature where we talk about black holes and stuff, right? But you take interior solutions, so you have an average density that is more than zero, but it's an average density. You will get a redshift from the center to any point in between and to the radius. Now, that being said, when you're looking at cosmology and we're looking out, somebody far away, the shining light here, that is going through a potential well, basically. And we don't know enough about the universe that there's a subtlety there of like, what is that density difference and how does that affect light? What portion of the of the redshift we see is from that gravitational potential? There's a lot of these questions that are unanswered. And so, and if you look at that metric and you look at how that shape is curved, it is sort of a parabola. So it at close enough distances, it could look linear, and it could start as it goes further, it looks like it curves. So we could be seeing basically a measurement where we are seeing that redshift due to things like how long the light takes and how much of the gravitational interaction of the rest of the universe that it is feeling, because there's a limit, right? If you're far enough away, the gravitational, there hasn't been time for light to, or for the gravitational potential to affect us, maybe.
So doesn't that mean space-time is nonlinear then?
That doesn't say anything about space-time, I don't think. I mean, once you're using relativity, you're already saying a lot about space-time, I guess, in one sense.
Well, it depends on which relativity, right? General relativity or special relativity?
General relativity. So you're already assuming certain symmetries, right? And by the way, I want to mention in my presentation that I didn't give the rest of it, and I've given it before.
I think that's all the butter we've got, Mikey.
Sorry.
There is another thing that was discovered, which is parity violation in the large scale structure of the universe. So, and that goes deep into the symmetries. So basically, general relativity does not have parity violation as part of its symmetries, and we see it not only in the microscale, but we see it in a large scale structure. So that is actually a strong experimental indication that Mendel Sachs is right about reformulating relativity with that symmetry removed. Okay, so anyway, that's my comment on what is brought up.
So I would like to add, if your epsilon and mu are changing, your speed of light is not constant. Okay, so we're talking about variable speed of light. And how do you trust your measurements? Because you don't know how that the properties of space have been changing. Unless you have a theory of how it is with time, then your measurements are sort of off whack.
So Brendan has a question too.
Sorry about that. I mean, it's just a thought and as a question. Yeah,
well, I'm not trying to shoot your question down. I need to chew on that one for a minute. But you're not wrong about the variable speed of light.
Okay, well, yeah. So come back to Mikolaj then, and go to Brendan.
Yeah. I was actually doing.
Sorry, I've got to think about things.
I was doing a download about this the other day, actually. but unfortunately, while I was making the recording, I forgot to turn my music off and desktop sound on my OBS. So like my voice was swallowed by music and I lost the recording. But yeah, I was looking into this, and apparently there's a discrepancy. There are discrepancies, Dan. But there's also not just between different camps and different telescopes. There's also discrepancies according to like what kind of standard candle they're looking at. Like, so I forgot what some of these acronyms mean,
Yes.
but there's the Cepheid variables, pulsars. There's also TRGBs and JAGBs, and they all fall a little bit different. Like some of them are in the 60s, and some of them are in the 70s as far as the that speed of H bar acceleration. But like,
If
and
you go
there's
and look into
also
some of those papers that I was, so if
I'm
you go
looking at I haven't taken a look at the paper yet, but
So
yeah,
if
go
you
ahead.
go down in the conclusion sections, they talk about exactly what you're mentioning right now about how we have these various measurement tools or objects that we use out in the cosmos. And that was one of the points that they were getting at is that if you when you look at any one of these standard candles, the discrepancy, the tension between LCDM and observation is only about, depending on what you're looking at, 2.5 to 3.5 sigma. That being said, when they start putting the data together from all of these various ones, the supernova, the baryonic acoustical oscillations, the pulsar timing arrays, the variable Cepheids, all of a sudden we're pushing up closer into the fours, and we're getting very close to the 5 sigma needed to say the flat LCDM model is probably outdated.
Yeah, there's also like a discrepancy between the methods. Some of the methods, like some of these.
No, Mark wants to go. He's got to go quick.
Yeah, the methods between looking, like some of these are looking at the center of the galaxies, and that is like sort of clumpy data. Like the Cepheids are like toward the center of the galaxies. They're trying to get the data out of the din in the middle of the galaxies, sort of that clump. And some of these objects are at the edges though, and so and the TRGBs I think were in the lower range, but those are coming from the outside edge. And it occurs to me that like when you're talking about redshifting, that could come from either acceleration away, but it could also come from gravity. And also according to Einstein, like those are maybe not directly interchangeable, but according to equivalence principle, which we talk about all the time, those are mathematically interchangeable. But that would not just affect the frequency of light, it would also affect the time dilation, which seems like it would affect the pulsation rate of the Cepheid variables. And is that accounted for in all their math as far as identifying what's a standard candle? That was my big question. Like, are they accounting for the time shifting in identifying these stars according to their pulsation rate?
They do talk about it in the paper, yeah.
Okay, like I gotta read the paper.
We should probably have Mark go. Looks like he has to leave.
Oh, yeah, Mark, go for it.
Oh yeah, I have to leave in a few minutes. So this is another update on the Mercury Vortex engine. The design is finally complete. I actually completed some of the cam work as well. So this is what it's going to look like from the outside. These are access ports for the wires. This is mounting bolts for the motor. This is, of course, the Mercury Vortex engine. Now, if we take that away, we take away the lid. You can see here this wheel shape. This is attached to the motor, and it has a little ring of iron and then magnets. And the iron is there to make sure that the magnetic flux goes farther out that way. And this is going to rotate around, forcing the mercury to spin around more. So let's make the let's get that out of the way. The motor and the magnets. Okay, so this is without that inner rotor in there. Now, if we take away the top, you can now see how the mercury actually is shaped. It's we changed the height of the mercury by changing the size of the depth of the of the chamber. And what this does is it forces the mercury to travel faster here on the left than it does on the right. And we'd expect an asymmetric centrifugal force pushing this device to the left. And I spent many, many hours working with it, finally getting the entire cam set up. So this is what it should look like when it's done. Get rid of the mercury. Yeah, so this is what it would look like when it's on this for the main base plate. This machining job is going to take about 5 hours on our CNC machine, so that's going to be happening probably on Monday. Gallium is very sticky material. It's not nearly as heavy as mercury, and it's also not as conductive as mercury. So yeah, it is safer, but it also freezes at room temperature and melts at room temperature too. Over here we have our vacuum chamber. This is the glass bell jar. We don't have it hooked up to the turbo because we are experiencing leaks. I'm pretty sure the leak is those two little ceramic guys over here. These guys. They made some crunchy sounds when I tightened them up, and they were already kind of broken when I got them. So that's probably where the leak is coming from. I have spare parts coming in. We're going to put some plugs in. We're going to add in an end connector for RF. We have high voltage ports over here. I think they're probably good for like 50 kV or something like 70 kV, depending on what kind of vacuum we pull. But this puppy over here, it's like almost 2.5 feet tall, and 18 inches wide, or no, it's more like 17 inches wide. So it's a pretty nice sized bell jar. We'll be able to run lots of cool experiments in there with high voltage, high current, and various sensors, that you may need. So that's pretty much what we have going on over here. Well, one more thing is the plastic that's going to actually become the mercury vortex engine. So it's already loaded up. And oh, yeah, also our S-band allophonic experiment. This thing is almost ready to run. Power supply for the electromagnet still needs to be wired up. We have a couple more things to wire up. The sample is in there right now, and it's stable. We're getting weight measurements from it. Vacuum, it was going down to -6 torr, so no leaks anymore. We got a new glass chamber in there. I may want to pull the thing apart though, because there is a side view port over here. You can just about see it there. And in that side view port, you're supposed to be able to see the sample. But unfortunately, when we put the thing together, there's a Teflon spacer that's supposed to go between the actual vacuum chamber and the chamber that chills it down to cryogenic. It was slided a bit too much deep in. So we're not able to see the sample anymore. All we see is Teflon. So we have, or Kapton. So we have to open it up in order to slide that back. The entire thing would have to come apart, disconnect everything and all the mounting parts and everything. So that may be a project that we'll be willing to do if it is deemed necessary. One more thing. Oh, yeah, just the fun never stops. So there's one more thing that we have going on over here. We actually have arts parts in this back room. Inside this big lead box over here, we have a gamma ray spectrometer with the arts part sample right up against it, and it's measuring for the any radiation that may be coming off the sample. We plan on running this test for the next 40 days. It's been in there already for a couple of days, so we're probably at like 35 by now. But it's going to stay in there probably till about mid-October, at which point we'd have the maximum amount of data that the device can hold. If there is any radiation from when it was picked up, by now it would be severely degraded. So we have to get the maximum amount of sample time data in order to determine if there is anything in there. If there was, is this a part of a weapons test? Those kind of questions are going to be answered via a long-term gamma spectroscopy test. So that's what we have going on at Falcon Space.
Thank you, Mark. That is awesome, man. You have a ton of stuff going on.
Thank you.
Okay, oops. How do I? There we go. I'll do remove spotlight. Okay. Actually, you have far more going on than you even shared there, too. And you've got the arts parts stuff. You're doing detailed analysis on that. SEM is done, right? And Jared is going to be presenting on the SEM analysis as well as the elusive, illustrious history of those. And then, sorry, Al Bauer's emoticon just threw me for a loop. Al, did you know that that's turned on? Okay, never mind. So
I gotta go, guys.
Mark, thank you again, man. Have a good one. Have a good one. Yeah, so over at Falcon Space, there's a ton of stuff going on. The arts parts, they're looking at Raman spectroscopy. They're trying to figure out what the crystallography, the crystal structure might be on those samples. Another thing that's kind of a possible is Jared Yates may have a lead on some other UFO parts, maybe, maybe not, and that's very uncertain. So he called it maybe 30% at best. So we will see kind of where that goes. But the arts parts thing, that's there. We're trying to do as much as we can. And my own pet feeling is honestly, like, we've probably reached the end of what's learnable there. I have a feeling that it may be at the point where it has to go out on a limb and somebody just has to connect it to this metamaterials idea. But that's just me. Who else has stuff for us?
Hey, Tim, I was going to talk a little bit about NSF.
Yeah, Dennis, go for it.
Hey, do you happen to know who funds Falcon Space? Very strange. I mean, there's a lot of things going on, and when he was showing all the radiation products.
Well, so Mark has several projects going on, so he will call him self-funded there.
Okay, fair enough. Because you want to really keep the government, having worked at NASA, keep the government out of that sort of radiation environments because they just put all kinds of restrictions on it for safety concerns. I mean, I don't want to go into it, tell you the truth, because it gets really, even small little pieces of radiation sensitive products, CCMs and things like that that really don't put out a lot of volume of protons or whatever it's spewing out, you know.
This is exactly why warp drive technology is classified under the peer review of the Department of Energy, because it falls under the atomic energy class, the classifications that the Atomic Energy Commission set up back in the 50s.
Yes, and but anyway, I don't really want to dwell into that, but what I did want to share is that I had participated with the NSF. I have participated for the last year and a half on a phase 1 project that's coming to the end in October. But part of the participation included a webinar that I attended called NSF, and actually it was only a 1-hour presentation, but NSF 50 to 100-year future technology. And the reason I bring it up because it was really my entry point into APEC. But I looked up a snapshot I took from that particular webinar, and I want to share it with you guys. Shoot, it's right here. Am I sharing, Tim?
It looks like it is not sharing yet. You may have to click.
Okay.
Yeah.
Let me see. Let me go back to the Zoom.
You have to select it, and then you may have to share again.
Yeah, I did select it. But, so, okay, I'm bringing it up here. Then I go back to Zoom and try to share. When I hit share, there it is. Voila.
There we go. There we go. Okay.
Yeah. So what was so strange about this is that I followed up with the presenter. He was a biz dev guy, business development at Momentum Space. And he was trying to say, yeah, here, propellantless propulsion is coming up. It's coming forward in the next 50 to 100 years. But really it's like almost here. But the point is that Jim Woodward's mock effect was put up there. He said that there was a NIAC, NASA NIAC phase 2. I know that brought up about doing an NSF SBIR on that on your instrument, and as well as Charles Bruller asymmetry capacitors in there in his presentation. But so I've only been associated with this particular APEC for the last 2 months, 3 months or so, and I just believe that there is quite a bit of lab work that's being brought that has been exposed and demonstrated here. And I just want to encourage, I guess I want to encourage people to look at NSF as a vehicle to bring your lab work, the work that you're doing in the laboratory, out and propose it and move it forward towards. And Curtis, I was trying to remember your name, Curtis Horn. That is a viable mechanism to move real lab work forward. And I can tell you specifically that in the cycle that I've been in for the NSF work, that there have been devices for quantum vacuum propellantless drives. There's been a warp drive grant that was given. And of course, my hybrid transfer vehicle, CAM drive, has been funded by the NSF. So all of these things are really viable, are opportunities that you can take advantage of. Commercialization really is being driven by NSF as well as the Department of Air Force and Space Force. They're looking for dual use technologies that'll support their missions. In fact, I'm proposing into the Air Force Small Business Innovative Research in this cycle, as well as I'm going to propose into the phase 2 NSF SBIR. I'm putting that together as well. But the key here is kind of interesting, and what I want to bring out is that what I observe from this group of people, from this ecosystem they call it, is that you're really embedded in your laboratory work. And the key here is that I want to encourage you to look at moving out of the lab and moving into some of the opportunities that are out there, NSF, the Air Force, and other opportunities that are out there. Because to be honest with you, personal experience now, that when you come out of the lab, it gets even more challenging. You want to know the truth. But also what comes out is your innovation comes out and gets developed in directions that you don't expect. And what I'm talking about is discovery. That if you really have a valid product, that out of using some of these opportunities, NSF, another government, DOE probably has another group of SBIRs that could be utilized, that things happen, that the discovery happens. And it's kind of funny, is that it's like a two-edged sword, if you want to know the truth, is that the fun, all the fun that we have, getting our hands dirty in the lab, kind of changes a little bit when you have to put the mantle of commercialization on top of it. But to really move stuff forward, move it out, there is, I believe, you have to use some of these opportunities. And one of those opportunities I'd mentioned to Tim was coming up. Let me see if I can even get to it. Is the NSF has asked for people to bring forward topics and ideas for emerging frontiers in research and innovation. And they have a whole program over that. And I was curious whether this particular group was interested in participating in that um, uh, it's not even a solicitation. They were looking for a 500-word description of a for a an ideas and topic areas that will move that could represent frontiers in research and innovation. To tell you the truth, guys, you're basically doing this. You really are. For instance, Curtis, you're if you took your current design and put it into a NSF SBIR, you probably have a better than 60 or 70% chance of securing an award, a grant. I say that personally. I say that because I've been on a couple of NSF panels where I reviewed proposals, and if you write a decent proposal with the level of technology that you guys are showing out at Cal State Fullerton, it would be a slam dunk if you want to know the truth. So anyway, I'm going to put in chat this letter for seeking topics for what do they call it? Emerging frontiers in research and innovation. Let's see if we can pull this off. Does anybody have any questions about commercialization in general?
Yeah, it's very interesting to hear what you're saying there, because I have been telling the group about the SBIR. The difference with the NIAC is that with NASA NIAC, Jim was doing that before I joined full time with the project. I was kind of like in the wings, like ancillary, like a lot of other people, monitoring it, interested in it. And the SBA, the NASA NIAC does not require a commercial entity, so it could be a university, be a nonprofit. So Jim and Hal had the help of a nonprofit, and that nonprofit is still there, helping out. And anyway, but for SBIR, for NSF, you do, like you said, you do have to create a commercial entity to get that funding. But that's not a deal breaker, right? That's like you said.
No, it's not. Oh, it really isn't.
We live in the real world, and there's certain ways of doing things. So we're definitely talking about that, and I agree with you. I think this project would be a strong contender. In fact, I'm not surprised to see that they showed Jim's work as an example, because he had gotten some NIAC funding. So that goes to show that there's some basic things there. I would like to discuss this further, because I know there's yourself, and I think someone else was on here that has done NIAC work. So speaking of like having a Slack channel or something where like we can have a team or some kind of conversation, this would be something that would be worthwhile, where those of us doing research, if we come up with something where it's now needs the next step. And from what I understand, the reason NSF, it's like a very targeted thing, what they want to fund. It has to be something that it's not an engineering problem you're solving. It's you're basically kind of still developing the technology, and that there's science involved. So there's risk where you can't get, it's harder to get commercial funding from somebody, because, who knows if the physics is right? So this is a place where, NSF can help out, and really, it's not a straightforward engineering problem. So definitely not that. And so, yeah, I think it is an appropriate funding mechanism. And you mentioned some other entities, and I think that would be probably for further stages. I think that would be something we'd be interested in.
I can say that. So when my company jumped into Vortex Space Systems, is my company, we jumped into the NSF arena. We actually proposed as a STTR, not SBIR. It was basically the Small Business Technology Transfer with Georgia Tech. Georgia Tech did the orbit analysis that we showed that we could actually do cheaper. We could do it more efficiently, do orbit debris mitigation cheaper, better. They also developed a guidance, navigation, and control system, which was preliminary, and we want to continue to pursue that GNC development as well with CAM drive and HTV. But the key here is if for Cal State Fullerton, you could actually a small company could team with them and create an STTR. And it turns out that, and I'm just finding out this recently, that the DoD, specifically the Department of Air Force, is really keen on STTRs as opposed to in small business innovative research. But the really interesting thing is from my observation with the APEC collaboration here is that there's like two or three items that could easily two or three innovative research products that could easily move out of your labs and move into NSF, SBIR, or STTR. I mean, there's no doubt about it in my mind. And like I said, in the current cycle that I'm in the last year, there's been a quantum vacuum drive that has been proposed, and I thought it was pretty rudimentary. And I'm not quite sure if he really even got his proposal or his product, his research out of the lab. I know that he did struggle with the commercialization of that research. And then there was a warp drive, which I thought, whoa, good Lord. How could someone propose and win a warp drive in NSF? Of course, I didn't say that to them directly, but I'm telling you that I thought it was very premature, not ready for prime time, if I will.
Or it could be the next Manhattan Project. You never know.
You never know. By the way, that's the key. Is it when you engage with my experience is when I engage with NSF, I thought my project was going to go along this certain way, and that's how I proposed it, and it turned out it took a turn, and that turn actually was a discovery. It was taking the innovation, pushing it through the process of experimentation, you come up with discovery, and that's what's happened. That's why I'm moving to phase 2. It was successful. But I really did want to bring it up because I see there's a tendency, and by the way, this was not the last time I'll talk about this. Tim had offered me to present in either October or November, depending on my proposal activities going on in the next couple of months. And I'll talk again about the value of moving laboratory experiments and innovation, basically moving innovation out of the laboratory towards a commercial product. I believe that intent, the intent of the government to support these sort of projects, is real and is viable and has value. That's my personal experience, and they back it. I'll talk real quickly some of the numbers. I just heard that NSF for phase 1 has moved up to $300,000 for a 10-month study, which is not bad. Phase two is now moving up to 1.5 million if you can get to phase 2. That's if you have the organization, if you have the product, if you have the innovation, there's governmental organizations that'll put the cash down. By the way, it's not easy. The proposals are not easy. The work's not easy. Well, you guys know the work's not easy. It's hard. It really is hard. But anyway, so that's all. That was my story. That's what I wanted to say, Tim. So I appreciate your time. Appreciate the opportunity.
Well, there's this discussion in the chat about the testing Michelson-Morley in space and all sorts of other stuff. It's like, I forgot who exactly said it, but it was Alex Gomez Marin, who has said, he had a brilliant way of saying this. He said that physicists should disclose their metaphysical baggage or their Bayesian priors, because being humans, we're subject to dogma, we're subject to beliefs, and a lot of it, it's we'd like to think we're all super objective, but they're not, especially when it comes to huge organizations and massive endowments and stuff like that. They're afraid of challenging well-established stuff because that would open up new doors. And oh man, we found a clean spot. Now we got to redo the whole standard model. They don't want that.
They don't want to risk their credibility or anything. So that's why.
Yeah. Well, does anybody else have anything to present or share?
By the way, that status quo is really the enemy of innovation. I mean, I'm biased on that one, 100%, because it is hard, really hard, to push innovation out of the lab.
It's ironic because innovation, that's what creates an economy, a GDP and all that. So that's what we need.
That's what you need. Yeah, exactly. It's worth the risk. It really is worth the risk.
Especially the military, they always need the best equipment, the best technology.
Always.
Yeah.
And that's a tactical and strategic advantage that they're always looking for.
Yeah.
Yeah, this is where like end stage capitalism becomes a lot like communism, and they're both of them have a tendency to limit the options rather than expand them. And that that it's hard to generate more GDP and keep expanding the threshold of your civilization if you're going through a collapse of ideas. So they should really open the doors more, for sure.
Yeah. Well, guys, let me see. So it's 6:30 Pacific time. And so I should see if anybody else has anything they want to share. We're not on a strict time schedule, but
I have a little thing. It's kind of a silly little experiment I was doing that's sort of like my own version of interactions between electromagnetism and electrostatics. I'm not sure what it proves uniquely per se, but I have a video of playing with magnets and balloons. If anybody's interested.
Yeah, if you want to share it. Hopefully don't get us in copyright trouble, but
no, it's my video. And I'm just gonna share it really quick. Hold on. So I think I showed something along these lines a little while ago, but I made a better video of the effect. And my family is all over the place, so let's see if they let me. Y'all see that?
Yeah.
Okay.
Yeah, that's coming through. Sure.
Okay. So I blew up this balloon, and then so I'm charging it up with electrostatic charge by rubbing a blanket on it, and then moving it around with the subwoofer magnet. And according to ChatGPT, at least, there should be small interaction between electrostatics. So there's nothing under the desk or anything, nothing weird going on. There's like I have speakers, but nothing directly under the desk. And hopefully you can see. So there shouldn't be this much interaction between electrostatics and electromagnetism, according to GPT. So I had to when you're talking to it and you give it something new and it does that memory updated thing, it seems that that's like in my experience, it's like a light bulb going over the head of the AI. It's like, oh, that's interesting. Oh yeah, at one point when I charged it up, it wanted to run straight toward my monitor, which I think that might be toward an electrostatics. But okay, we'll let him because I'm doing this. So I charged that up. I'm literally doing a presentation. Okay, so this is me. So you can see how it turns and sort of follows it. mainly at that like the end of the balloon. Well, it was stuck in the wall. It was originally the tie was the one that was going toward the magnet. But in this case, it seems like the strongest attraction was toward like the end furthest from the tie. I just kind of played around this for a while. Let's see if I can get any kind of turning it. I forgot the name of the gentleman that was playing with electrostatics. You could see all the dust on my desk that got picked up because my office is filthy. But it seems like the more it accumulates of actual particles, the weaker the connection gets. Like it sort of evens out.
Did you try the same experiment using neodymiums, so a more powerful point source of magnetism?
No, I don't have any of those handy. I know it's a terrible excuse, but I might do another video where I try different magnets like that. It's a good idea. Anyway, I won't play this forever. I think you guys saw what happened clearly enough. Let me know if you didn't, but that was just I started playing with that because of reading about T.T. Brown and the asymmetric capacitance between areas of high electrostatic charge and high electromagnetic charge. And I see Ken has his hand up. Is that a question for me, or are you wanting to go next?
I wanted to go next.
Oh, okay. Anybody else have any questions or insight on what the heck his guess that the machine had for me was that it was the movement of electrostatic charges across the surface of the balloon might be creating eddy currents that were interacting with the magnet. Well, it didn't say anything about polarity per se. I'll try to get my hands on a neodymium that's clearly marked for the south and north poles. Otherwise, I'll find a way to test it.
There for quick and dirty, there you can. It's available on Amazon from AZ Industries. They have this little plastic pole indicator. So there's basically a magnet in there,
right?
And a little window, and in the window you can either see it say N or S.
Yeah,
That's
I've
the
heard of
way
those.
to unambiguously figure out what it is versus going and winding your own coil and saying, okay, this is the North Pole, or getting out a compass and figuring out that way.
Yeah, I'm at the very beginning of my experimental journey. I don't have a lot of kit yet. This is just my attempt to do something with the materials I have on hand. But as I go, I'm going to get that. I'll get one of those and a few other things as well.
In fact,
I would appreciate
I
it.
should have it within, no.
Yeah, I've seen those before. People have used those on I've seen people use those on rodent coils to show that there's only one.
Yeah, that
Seems to
something's
be
going on. I don't know
only
where
one pole inside the rodent coil to kind of demonstrate the monopolar aspect there. But anywho, I'm done making a poo of myself. Thanks, guys, for indulging me. I'm done, Tim.
Hello?
If you want to go to the next peeps.
Yeah, sorry about that. Okay. I got booted out. My child was trying to call me from the house and it confused my computer. So let me see. Ken has his hand raised. Ken, go for it.
Right. Well, I was going to prepare some graphics for this maybe in a few times, but this is a simple question I'd like to pose. And maybe some of our relativity experts could answer the question for me next time. I used to work for Draper Lab, and I designed gyroscopic integrating accelerometers. And they are, in my opinion, perfectly capable of very accurately measuring inertial acceleration in whichever direction they happen to be pointed in. And that's of course, one subject that if others are not familiar with, I can do a presentation on sometime. But the question is this, and it was actually not mine, but I read something similar in Paul Hill. You're familiar with unconventional flying objects? Paul Hill was a NASA engineer. And he posed the question of, let's take you're in a spaceship and you're going in a straight line to your destination. Now, you're measuring your acceleration using an inertial accelerometer. You also are propelling your spaceship using energy that you derive from the ether or the vacuum or whatever you want to call it, which I believe a lot of you at least hope is possible. So in other words, we have this spaceship being powered totally independently of anything except for the ether. You're measuring your acceleration using an inertial accelerometer, and you accelerate from 0, let's say on near the Earth, and you continue accelerating until you get up to 0.99, the speed of light. Now, Paul Hill says, and I tend to believe with him, you don't turn into a pumpkin when you finally hit the speed of light. You continue going. And there seems to be no reason why you couldn't continue accelerating to 2C, to 3C, to 4C. Now, this has not, it's special relativity if you want to talk about somebody observing you from a different reference frame. But I'm not. I'm talking about my reference frame inside the spaceship, going in a straight line, accelerating using energy derived from the vacuum. Is there any reason that that cannot continue to accelerate to as fast as you want to accelerate to? So I don't expect anybody to know the answer, but I'd appreciate it if you think about that and perhaps discuss it in detail next time. That was the question.
My research indicates that the reason you can't go past the speed of light with conventional means is because it would take more energy than exists in the entire universe because of the Lorentz invariance. Like it just doesn't work. Like yeah, but I mean, that's not to say anything about warp drives or wormholes that apparently can allow for that. But the problem there is the positivity conditions and that you would need technically negative energy, but we haven't found that yet. We haven't been able to create it yet.
Well, realize
although we talk about
better.
we talk about that.
Disagree. I mean, all that stuff has been found. I think that the so-called speed of light only applies to the light. And light and gravitation are two different things. Inertial energy and light are different. Light photons have no mass. Without mass, you don't have inertia. And that's a good segue into what the question was I was asking at the beginning, which is space-time linear or not? If it's not linear, then faster than the speed of light is totally feasible. And so is slower. The speed of light, you can do stuff slower. I mean, matter slows light down, doesn't it?
I mean, isn't classical general relativity considered non-linear?
But yeah, general relativity depends on the speed of light, depends on where you are in the universe and what the space-time continuum is you're in. And the reference between the two space-time continuums they affect it.
Yeah, I was just dropping the textbook, as far as what the typical answer would be. This to say nothing of all these other attempts to do lower energy warp drives or warp drives that don't violate the positivity conditions or requirement for negative energy. But Dan Davis knows way more than that about me than that.
Conditions, which are actually assumptions, by the way, which nobody ever talks about that.
It's a fundamental assumption, though, that you're drawing energy for propulsion, not from conventional means, but from the vacuum. Energy from the ether, so to speak, which, again, I think everyone would like to see sometime. I'm sure, well, it hasn't been done yet, but at some point, hopefully it will be. And then that brings up the question is, if you're not worried about, I'm sure that a stationary observer, which is watching this spaceship, is going to see you go up to the speed of light and no faster. But I'm not talking about that. I'm talking about you inside the spaceship using an integrating accelerometer and time, a clock to tell you exactly what your velocity is. And that's what you're going to see. You're going to see it go up in a linear fashion. If it's a constant acceleration, you'll go through the speed of light and just keep on going. I don't think you're going to all of a sudden hit a brick wall or turn like I said, turn into a pumpkin.
It's an event horizon. It's a virtual event horizon. It's like looking at a still piece of water at the right angle. It looks like a mirror, but if you look straight down, it doesn't. That's an event horizon. You can't see beyond the event horizon. It's kind of like Mike McCullough's theory.
See, there's some chance like
quantized inertia.
From your reference from you inside, for you, time would continue to move forward just so. But as you go past the speed of light, let's presume you have a faster than light drive, the rest of the world, the universe might start moving backward.
Exactly.
To you. You're moving backward through time.
From their reference frame, that would be true.
So there's a whole thing with the positivity conditions, which is that they put those there so that you don't end up with solutions like reverse causality, because that would break the space-time continuum, that would break causalities as far as we know. And then, that gets you into multiple universes. So I personally think, we have this debate all the time in my Discord, but I personally think as soon as you go backwards in time, you're creating a branch of an alternate universe. Because if you think about it, you can't go to your own past without making a new branch, because you've all of a sudden modified the universe.
But that's assuming that time is linear when it's not. Time we exist in closed time-like loops. It's closed time-like loops. That means that we go back to the past and we go to the future over and over and over again. It's like the movie Groundhog Day.
Yeah. Yeah, I think that conventional wisdom has it on a forward line sort of trajectory, but I think it's far more accurate to think of it in loops, or maybe like a tree with different looping parts that loop back to other parts that continue a ways.
If you're going backwards in time from your reference frame, you're not. You're going forward, you see? And that's that's the nature of quantum entanglement too, because that's what's going on in quantum entanglement, the same exact thing.
Well, let me ask
I think we should all read Dan Davis's temporal compendium. It's full of this. I think Barak Shoshani has more to say.
Let me ask you another question. If there were multiple dimensions or universes or whatever you want to call it, do they all share the same ether?
It depends on what you mean by ether.
I mean the magic vacuum that is full of quantum foam. Is there only one of those, which is housing all of these multiple dimensions, or are there multiple
Well, so what
dimensions.
do you even like? What do you mean by dimensions? Like space dimensions, time dimensions, dimensionalities, and Hilbert
No,
space?
I mean
You
like
So
have
in
to be very
string
specific
theory,
when we're going to get into
in
this.
string theory,
multiple. Yeah.
there's 11 dimensions. Okay,
Which
one of
version of
which
string
is
theory? M
time.
theory, superstring
So
theory?
in string theory, they have what's called compactification. So
Yeah,
that means
you're
that
trying
there's
to
like
compactify, get rid
dimensions
of the while anomaly. Yeah.
change when you get closer to something like matter, right? And so string theory works with general relativity. The problem is it's so mathematically complex that there hasn't been any experimental data to show that it works. So, well, try doing an 11 dimension tensor. Think of it like that, okay? It's just like, and then you start talking about the units of the dimension, like 10 to the minus 35 meters, or how about 10 to the minus 31 seconds? Okay, that's not feasible to measure, but it turns out that Planck mass is a whole 22 micrograms, which we can make stuff 22 micrograms. We do it all the time in the lab. And that's exactly what I did in 1998. And that's what my patents are on. Okay. And that's how I know that this stuff with what you're talking about going faster to the speed of light, is possible because I measured it and I could show it. Okay. I could show you the data if you want to see it. I
Oh,
can share it with you.
I'm personally not arguing against
No, I
superluminal
don't want to
phenomena.
argue.
No,
I want a
I'd love to
dialogue.
see that.
So, like,
I'd love to see the paper.
I'm in favor of superluminal phenomena. So I do want to put that qualifier out there. And I am sorry.
Okay,
Yeah,
I'm going to
this
try
is
and
my
do a
jam too.
share screen here.
Do you need to go out, dog? I am so sorry.
So can you guys see this?
Yeah, I could see that.
Yeah.
Okay, so here's my test bed. Okay, I put little nano bumps and nanopits on the surface of a hard disk platinum. And there you can see on the left, there's a little blue. That represents data that's written on there, which are as magnetic domains, one north, one south. Okay, and this little head device that reads back the signal. And so what I did is I made this. Let me close this down to there. Okay, and so this is the little. It looks like a sled, and it's like the disk is rotating, and they say that it's the head's flying over it, and this is distance between here. That's called the flying height. This between the surface of the disk, and then there's this little sensor on the tip of the thing. It's called read write, and I'm using this thing called GMR, which stands for Giant Magnetoresistor Sensor. So now what I did is what I have here is it's a magnetic force microscope made an image of one of my nanopits, okay, and it measured the magnetic force in nanonewtons. And so below this, though, I have this image of a disk drive, what data looks like on your disk. It makes these little magnetic domains. And so this, on the bottom part here, that's your data. And then on the top, there's this thing called a servo writer. It writes this pattern that kind of orients your disk drive so you can tell where the data is. Yeah, show you. So what's going on here though is, let me find the right equation first for you. Here is it. Awesome. Have this equate. I'm looking for the tensor equations.
This is your most recent paper that you put up on
Well,
ArcShift,
this
right?
is the preprint of the paper. I can't
Which is
put
super
the
interesting. I'm just curious what this has to do with faster than light
so
travel.
well here I'm going to talk about it. Okay, now Hal Puthoff, you guy probably know about him.
Yep.
He did this paper called metric effects on not what hold on.
Advanced space-time propulsion based on vacuum-metric engineering.
Advanced space propulsion based on vacuum space-time metrics engineering. That's his paper. Okay, and in that paper, basically, he has these variables are a typical stellar mass. You get close to a stellar mass. The other one is space-time metric engineering or engineering the vacuum. Okay, and what's going on is in the typical stellar mass, clocks run slower, and in the vacuum they run faster. Okay, in the vacuum, when I say in the vacuum, I'm talking about outer space. Okay, away from Earth. Okay, what happens though is with the frequency of is the redshift towards lower frequencies when you're in a higher mass, or what I call a denser space-time region, or blue shifted in an expanded space-time region. Okay, like outer space. Energy states are lowered or energy states are raised. Rulers shrink in the denser space-time, and objects rulers expand in the expanded space-time. And now the velocity of light, we're talking about the effective velocity of light is less than c when you get closer to the mass. Effective light is greater than c as you get away from it. Same with effective mass. It changes depending on the space-time you're in. And same with gravitational force. It's gravitational when you get closer to the mass. It's in expanded space-time, it's anti-gravitational. So does that mean doesn't that mean that the so-called vacuum is pushing back from the future? So basically, what Puthoff talks about is you have this thing called a four-dimensional line element, and in Cartesian coordinates, it's expressed like this equation 3, but in spherical coordinates, it's expressed like this equation 4, and that's relevant because we're dealing with a rotational frame or polar coordinates. So the z coordinate is basically irrelevant. So now what happens is I'm going to skip past this equation and show an example. Okay, now there's this guy. His name is Gödel, and he had this. He had a solution to the field equations that suggested that time travel was possible. In Gödel's universe, everything is rotating, and this rotation creates paths in space-time that loop back on themselves. These loops are known as closed time-like curves. And in this, so he's assuming though that that you have to go faster than light. Basically, you have to be the angular velocity has to surpass the
yeah, you need to go superluminal in order to go
to go to it, right? So, but what I found is that's not necessarily true. But here's a representation of his
yeah, well, so what you have to consider about that the whole Gödel metric thing going on is that you're never locally going faster than the speed of light. It's an effect of the frame dragging going on with how the universe is rotating.
Exactly. Well, I don't know about that. It comes back to the question: is time linear? Okay, but theoretically, what it says is you can go back to the start point, and the end point can be basically entangled.
Yeah, the future infinity and past
So,
and
but
Bouchard.
to
They're
test
identified as
that,
the same object on the Clifford Torus. Yeah, it's
so
just
what I'm doing now, I'm going to skip around a little bit to a couple of. Hold on, I got to shrink this down a little so I can find myself a motion. Okay.
Center, yeah, there.
Okay, there.
looks like Curtis has a question too.
Yeah, hold on. Okay, here's my what is here?
I have a question. Do you have a link for the for this paper? What was it?
Yeah, sure. I think I put it in earlier already once, just so you know.
Oh,
So
okay.
go back and look in the chat from earlier. It's in there, but I'll do it again when I'm done. Okay.
Yeah.
So basically, here's a nano bump signal. The GMR read head signal of from a 10 micron by 10 micron square bump, 32 nanometers tall on a hard disk, spinning at a linear velocity of 500 inches per second, or about 12.7 meters per second. Now you can see here, there's this disk is turning counterclockwise. So the first pulse on the left, that's from the electromagnetic induction signal produced by the edge of the nanobump as it hits a 90-degree phase change in the magnetic field direction at the edge of the bump, speed of light. Okay, and then that's followed by this gravitational induction signal produced by the nanobump. And you can see it's interesting that you'll see there's texture on that part of the signal because it's got a surface texture. Now that's followed by this second electromagnetic induction pulse from the other edge of the bump, 0.8 microseconds later. So now I'm going to show you, we're going to do this again. Now this is cross-sectional view, shows, I'm going to blow that up a little here. It shows the, basically that we got our disk spinning, okay. We got our nano bump there in orange. And then the GMR sensors, as I showed earlier, it's on the tip of this, the edge of the slider, it's called. So it's like a sled. And then on the back, that green thing, that's a piezoelectric crystal. And a piezoelectric crystal, if you tap it, it produces an electric pulse. It's a physical force sensor that they use in accelerometers. And they make an accelerometer as a piezoelectric crystal. So what we're seeing here is when the bump goes over underneath the slider, it pulls the slider, actually physically moves down. And this is on the right, that's the sensor from the GMR readback signal. And you can see those little magnetic induction pulses, right? And the gravita now so basically think of the Earth's gravity is pointing down and this thing pulls it physically. Now, what's important to note about that is if we go back here to where was this guy, these little magnetic force. I mean, I measured the magnetic force with the magnetic force microscope of those little magnetic domains. But those magnetic domains don't wiggle the head. It doesn't physically pull on it. So as far as inertial energy goes, it's virtual. There's no inertial effects. You follow? So that's how I know it's electromagnetism and not gravity. Now let's go look at the nano pit. Here's our nano pit. So again, we have this same little 10 by 10 micron square nano pit. And same setup. And we look at the sensor, the mechanical force sensor here on the left. It has a push signal. It's like The polar gravity, it's pushing against the polar gravity. That's why it's like a totally dampened signal as compared to the bump, which was like an undampened signal. And now we look at the GMR signal, and again, we see these little electromagnetic pulses in the right place. But then now the gravitational force signal is in the opposite direction. It's a push. And that's image. That's what that's actual data from the nano bump and the nano pit, the 10 by 10. So essentially, now I showed you hold on, the boss is calling. Well, maybe she'll give me some peace.
So I noticed in your.
I'm trying to get to the punchline here. And then,
okay, I'll let you get to your punchline.
Okay, so now here, what we did is if we assume this first, what I did is the put-off model predicts that clocks run faster in expanded spacetime and slower in denser spacetime. Let's assume the speed of light is our fixed time reference, with gravitational interaction time as our variable. The magnetic induction pulse shown on the left in the two figures is time t equals 0. With expanded spacetime, which we're looking at here, time shrinks and length dilates. So an anti-gravity pre-signal is expected. And we see that, see? To a non-expanded spacetime observer, objects moving in expanded spacetime appear to exceed the speed of light. Obviously, to the expanded spacetime observer, everything's hunky-dory. And then the opposite's true with denser spacetime. The theory predicts that with denser spacetime, length shrinks, and so a post signal would be expected. A post signal is observed. So I'm seeing this. This is in the actual data. These what I would call general relativity effects. So now, has anyone got some questions? You want me to leave this up, or
that's awesome. My question is around sort of a subtle but important difference between the speed of light and the effective speed of light. Like,
okay.
So, from your point in perspective, it seems like this is going past the speed of light, but that you have time contraction in one direction toward you. So,
Brendan, pardon me, my significant other.
Okay.
I gotta stop.
Yeah, so we'll stop that. Well, Michael, thank you, sir. Thank you. So I should see who else. Curtis had his hand up again a moment ago. Does anybody else have anything?
I might, but I'll wait till someone else wants to go first.
I just have a little question for Michael Boyd.
Yeah.
So
I can't hear you though, Phil. You're kind of quiet.
Yeah. Well, what is the gravitomagnetic permeability value you're using?
The magnetic permeability is the same. It's just it's how the magnetic field is affected.
The gravitomagnetic permeability.
I don't. I guess I don't follow your question then. Are you saying it's different from if the permeability was different, I would think it would have a fixed value. Do you know if there's any papers on that being measured, the gravitomagnetic permeability?
Okay, so you're not
I'm not familiar with that, no.
Okay. All right, thanks.
See, I mean, permeability comes into what's called mobility. In the like semiconductor physics, you have it's called mobility, and that's one of the terms in mobility is the permeability. But it's like and it's related to the speed of light. I think it's the square root of permeability times permittivity or something like that. And so yeah, it's related. But so if you're in matter, the permeability, the speed of light's slower, and if you're in outer space, speed of light is faster. Is essentially how I look at it. So that I would assume affects the permeability, and the permittivity would adjust accordingly, wouldn't it?
Yeah, okay. I was just wondering your opinion on that.
Well, I
So
guess
are you talking about the modifying general relativity to account for a different speed of light because of the refractive index? Is that what you're talking about? That's Jack's theory.
No, it's more, it has to do more with where you are when you measure it. Okay.
So
So,
I guess the question that I have is a little bit more practical because you've been shopping this one around for going on 4 years now, right? So what kind of physicist feedback have you had on it, and what kind of like hard and fast predictions have you been able to make? I mean, like, because I know that you're talking about the needle and stuff like that, but it is one of the things with theories like this, right, is the power of predictability is really important. And I think another thing is from a self-sanity check, you need to be able to either prove it or move on. But if it's in limbo, when you keep shopping it around, that's like, then that means you can't really do that much with it, right? You're kind of stuck. So,
yeah, I would argue that I had to prove it to get it through peer review. And,
and so
and,
that's the upcoming paper.
and that plus the substantive evidence that comes from all the peer reviewed journals that are referencing it.
Okay.
The basic premise comes not from me, but from Hal Puthoff's paper. And yeah, if you look at Hal Puthoff's paper, he's dealing with permittivity and permeability there too, right? So basically, I have uh, a, inductive as opposed to a deductive approach. Deductive is you have a theory like string theory, and you hunt for data to make it fit. I took the opposite approach. I have a bunch of data. How do I explain it? Okay. And I found this paper by this guy named Hal Puthoff that seemed to fit.
Yeah.
So it's not guaranteed that Hal Puthoff's paper or his theory is complete. It could be incomplete. And in fact, that's what Jack Sarfati has argued, that it's not complete because of within the near field, it's not complete. It's only applies to far field effects. So that's my interpretation of, and Jack could be totally right, but I don't have any data to support that because I haven't did anything in the near field.
Yeah.
Right. It's kind of like the whole Tic Tac thing. You can look at the Tic Tac videos and see all these far field effects that make sense.
Well, so it sounds like you have to wait for peer review. You have to wait for this to come out a publication. That sounds like that's kind of the next step, right?
Well, no, it's already come out. It's already been published. No, the preprint is just because it's $35 if you go to the IEEE and try and buy it. It's $35.
Yeah.
That's why I sent my copy around to a bunch of people because you would have had to pay for it. And I can give it to you for free, but I can't publish it. Right? So it took me a year. It took me a year. I mean, I was talking to you guys about this last year. And so
yeah, so take a look at this here. Can you see it?
Yeah.
Yeah, and I have two other hands up too. But yeah, Richard,
So
I can sort of see it. You're out of focus, but I see
yeah,
a
here we go.
Yeah, I think
magnet.
Jeremy's had his hand
Yeah,
up for
so
quite a
you could
while.
see
Yeah,
the
and that's
the curves in here.
mm-hmm.
Okay, and then there's a hole in the center, and then on the side there's
That's a
induction here.
centrifugal fan blade.
Right, right. And then on this side it's flat. So if you look at the vectors, if you're pumping this way, then you can compress the molecules coming out here. You can charge them, you can heat them. So I think that is, something to. I'm kind of been pulled into the idea of building something here.
Okay.
So you could create a high volume of pressure here, although the vector will try to load up along here because you only be able to push so much here. So there's some physics going on there.
Well, yeah. So if it's okay, let me go to Jeremy really quick. Jeremy has his hand up. So Jeremy, what is it? What is it that you've got, sir? And can you?
Yeah, I basically found this thing about light in the paper. Let's see if I can find it here. It's like, oh yeah, evolution of the electric fields induced in high intensity laser matter interactions. So
Is that something you can?
just basically.
Oh, okay.
Oh no, it's there. I put it in the thing so people can download it. It's like femtosecond lasers, extremely high densities, within form will accelerate particles to relativistic and G4 distances. Well, I found a paper that they said, one article just recently that they managed to get an electric field to interfere with lasers, and I said that the electric field actually manipulated the laser itself instead, like I guess from a lower energy state. So,
okay.
that did anything. That was
Maybe
pretty cool.
Could you drop that into chat, do you think? Maybe you could drop a link
Yeah,
to
I
the
did.
paper. Did you? Okay.
Yeah, it's right there below where I said you have a link for this paper, and it should be Science Directs SO1689002218218.
Yep. Yeah, I see it.
Yeah.
I see it. So what I'm going to do is I'm going to copy that, and I'll just put Jeremy's paper. So it's in there twice now.
Yeah. What I wanted to get at is that I'm more like realizing everything is more just purely light based, as you could say. That it's like there be perturbations of, I guess I still stick with the vibration thing. I don't know why, but to me, like light is just like just another mode of vibration. It's just you just see it differently, and I would think matter even itself is made of a standing wave of light. In my opinion. So, like, if light could change the chemistry of things, any solidarity object that we call like matter, that would revolutionize a lot of deals. Just recently, they just gave a video out about a certain lens that could look beneath the humans. Well, I guess can't get that, so I don't announce it. But they discovered something that would transform that. It was an old type of thing in the 1940s. I think they did. So, but
I'm just scrolling through your video right now, or scrolling through the paper right now, and I had to put the new link in there.
Oh, okay.
It says, in conclusion, we provide femtosecond resolution measurements that allow to operate on the same time scale as considered process determined by the driving pulse. We've revealed temporal evolution of EM pulses with lifetime of several picoseconds. So
I don't know if this is relevant to anything new. Just found it was kind of interesting that electric field would mess with the laser instead of the other way around. So if you're talking about lower energy states affecting higher energy states. So
Yeah.
other than that, that's all I wanted to give out. Especially
well, thank you.
Yeah, especially if they get like I'm almost done. Especially if they get like like the radiation of a star, if it like I guess get it from the sky, you could like somehow capture the signal, maybe like put it together, maybe you could generate power from a star from a mass distance, despite the distance. So I guess fixing the signal. But that I guess that requires a lot of mathematics. If you get what I'm saying, so. Better than that, I have to learn more, so I'm really be quiet now.
Okay.
I want to throw that out.
Well, so Jeremy, thank you. Let me go to Curtis, who has patiently had his hand up as well.
Michael, can we go back to your paper? I'd like to, and you
Okay.
had a chart there where you had a
Sure, hold on.
gravitational versus metric.
I got it.
And we have about half an hour left, I think, guys.
Sure.
My caffeine levels are running low. You could probably see that. I'm starting to
My
fade
wife's
out.
patient's the same. Let's see here. Share screen. Right there.
So,
okay,
you have a chart there where you had gravity and
Hal Puthoff's model.
Who's
there it
right
is.
now, you just passed it on the right.
Yeah,
Very
I
cool.
got it. Hold on.
Like if you can.
Sit down.
Now here's the thing. So if you have a traditional stellar mass, right? The redshift is if you're shooting light out and you're out there, you see a redshift. But if light comes in, you're going to get blue shifted. So everything's relative.
Yeah, exactly.
Now gravity itself is known to be positive definite. So
what?
Positive definite, meaning that it's always just most of the things we encounter.
Are you saying it's only one direction?
Most of the things we encounter are attractive. Now, in general relativity, there are metrics where things can get flung out. And so there are metrics like that are like that. I would caution people taking shortcuts with general relativity and putting much stock into that because like what we're talking about with cosmology, there are a lot of shortcuts you can take and not use the full equation. So people go in cosmology, they say, okay, well, there has to be new physics because our models show that something else is going on, hence dark matter or dark energy or what have you. And when you go look at the details, they are taking linear approximations. They're using Newtonian gravity or some kind of model.
The devil's in the detail.
It's not the full nonlinear GR, right?
Right.
So I would be very cautious with these kind of statements because there's more to the story. That being said, I would encourage you to look at my talks and fundamentally, I mean, really, like I look at when I looked at the stuff Hal Puthoff and others have done, and Jack that you mentioned, I see that as okay. They're trying to describe a phenomena using kind of known physics and what they understand about it.
I agree.
Whereas what I'm bringing up is somebody just doing physics and as a side byproduct of what comes out of it is a potential explanation for these things. So it's a whole different kind of deal, right? So if you look at Sachs's work and his hypothesis of background pairs and all that stuff, it sounds like a lot like an ether. And when you have an ether, you have a a media for that kind of thing for you to play with that, right? So then these things come into play. So, but what I want to mention specifically is the big difference with GR is that GR is completely symmetric. It has parity and time symmetry embedded in the theory, right? it was something that Einstein put in because at that time we thought physics, if you run it forward, run it backwards, it's the same. And if you have parity left to right, your experiments are going to be all the same. Since 1956, that's been proven wrong.
Yeah.
Okay. So
yes, time isn't linear.
okay. Well, you can use the word linear, but okay, this is a symmetry. So now we know there's something called CPT, right? Charge, parity, time. That's a symmetry that's held. So GR, now GR, if you take GR and you reformulate it with those new symmetries, you get something like what Sachs developed. And what Sachs developed now has, I mean, that formulation of general relativity, what comes out of it at a low energy approximation is what we have with quantum mechanics. Okay. That's just how it is. That's just the math. It just comes out. It's there. For decades, people ignored it because it's like, no, parity violation is a weak force. It's only in the small scale. And this is why I got back interested in the work Sachs did, because 3 years ago, and I put the links in chat, the observations we have of the universe show parity violation at the large scale structure of the universe. So now we're now having experimental evidence that there's violations of GR, and it's not these things of like, oh, here's a UFO, okay, I can back figure out what that's not going to work, right? There has to be a fundamental physics reason why, and we have to understand it. So the symmetry breaking and making your theory the right way with what we know now experimentally is what I would suggest. Now, the other thing I would suggest is take a look at in my other presentations. I showed these experiments with neutron diffraction. Okay, and with neutron diffraction, they see with neutrons diffraction, right? That's a particle, basically a particle physics experiment where you're taking neutrons, you're diffracting them, and you can see an interference pattern. And they see an interference pattern where one part of the neutron wave goes up in the gravity well versus goes down in the gravity well. So there is an interaction between inertial mass and gravity, and it's there. It's something proven. And in fact, that same experiment, this is something that Carver Mead was in his presentation back last year in the Kyoto Prize. It's something I put in my slides, the physics slides. And I could show that to you, but you can go back and find that. But they also did that experiment where they took it at an angle as the Earth rotated, right? Rotated around to see if there's any, like if the neutrons knew where the rest of the universe was, right? That's kind of like a Newton's bucket type experiment.
Mach's principle.
Yeah, and it did show that there was a difference depending on that angle.
Sure.
So
depends on where you are.
Yeah, we know matter knows where it is, knows where the rest of the universe is somehow, right? What that coupling is, the answer of the mechanism, that coupling, that's like the secret sauce that we all want to know. And there's hints to it, like you're saying, like what Sarfati and Puthoff have mentioned. They're kind of like talking about it at a level of like a quantum level of like, okay, there's an effect there, and we see that effect. What I'm talking about is really the mechanism. I'm trying to figure out what the physical mechanism of that, how is that happening? And the way I'm going about it is I'm trying to figure out, okay, what's fundamental, and let's reformulate physics from what we know is fundamental. And right now, it's looking like quantum is not fundamental, it's emergent, based on Eric's work.
Okay, thank you. I appreciate your comment.
And so,
I would appreciate it if you have any links or anything. Like, didn't you do a APEC presentation?
Yeah, I've done 3. So if you go see
you
those,
could just give us in the one you like, the date for the one, and then I'll go look it up online. Okay.
I think it was last October, 2023.
October what?
2023.
No, what month? Weren't there 2 back then? Weren't there 2 months back then?
Or was it was October APEC.
Okay.
Not the Open Mic.
2023 October.
Yeah.
Okay. Well, thank you.
Now that being said, I'm not saying I know the answer. That's where I am now, right? So really, I think what we really need to do is be honest and look at and say, okay, what do we think is fundamental? Is there an experimental violation, or is there some limit, right? What is emergent, what's not? And really with so I have been looking like recently at other theories, like a lot, opened my mind and started looking out there. I found John Williamson's work, which is somebody mentioned matter being like light turning in on itself, and that's what that whole basis of his work is. And unfortunately, we lost him like recently. I reached out to his group, and I haven't had a chance to meet with him. My life's been crazy the last month, but there is. It's really interesting because the equations he derived end up being very similar to what Sachs's work comes out of Sachs's work in terms of a spinor quaternion theory. Now, in terms of like what is fundamental with the algebra and what's emergent, that's a big question, because we do have the Standard Model, right? That's a high energy. At high energies, whatever theory we have, we need to be able to say that at high energies, that theory produces those predictions, right? So whether those predictions are fundamental to the space-time or whatever you want to call it, to the fundamental stuff, or it's something that's emergent that comes as as consequences of adding energy and having all that shock and awe that goes on with these colliders. That who's to say, right? We have to explore that. But in terms of the fundamental physics theories, right now, my opinion is GR is kind of on shaky grounds because of these parity things that we already know, right? And quantum is also in the same way. It's like there's places like when you have low energy matter, it's how low energy matter behaves. We know that, right? Quantum effects are like they're apparent, okay? But once you get higher energies, in that type of regime, things start going off the rails. So I'll give one more example on that is the nonlinear Brett-Wheeler process, right? So that's the one where you can have laser light and you can have a gamma ray and you get a pair production, right? A positron and anti an electron and a positron produced. So that's not necessarily something that was predicted, right? That's something that later on they calculated, okay, here's a way to get that with QED.
Yeah, I agree with you. There is one thing that I did get out of the geodesic curved spacetime was probably an upward thrust. And then if you have this ellipse-shaped object, you should probably move in the curve one way or the other, whichever way you control it. So that's one thing that I did get out of it was a coordinates, because I think he was referring to coordinates. But as far as being realistic about relativity, I think you're right on.
So Michael, just curious, have those experiments been done where like they're pointed in different directions or anything like that?
I don't understand the question. What's
the experiments you've done with that rotating hard drive and where you had that pulse?
I've done it.
Is there any difference with the angles? Did they do any of that kind of?
Well, the disk is the nanobumps and the nanopits are on the surface of the disk. The disk is totally level.
Okay. So
Right.
they probably didn't change the elevation to see if that would change the timing or anything like that.
Well, no. When I did the measurements, I did it at a constant linear velocity, so it shouldn't have been affected by the velocity, for example.
Yeah.
But what if you had done measurements with it perpendicular to the ground? So in other words, you have it face up. What happens if you do 180 where you have it spinning the opposite direction, still parallel to the surface, and then what happens at 90 degrees, or if you orient it vertically, doing any kind of sweep from 30, 45, 60,
Yeah,
et
no,
cetera degrees.
the test bed is this thing called a spin stand, which is a spindle that turns around. I could measure from with the bump on the surface or the bump on the bottom surface.
Okay.
Okay, but the force direction remained the same whether it was a pit or a bump.
So I'm just curious about it because it sounded kind of like similar to this. I don't know if you can see my screen, but these are the slides that I took of the neutron diffraction experiment from Harvard.
Oh yeah, I remember that one.
And so this was the one where they basically rotated it around so they could see that there was
Oh, I see what you're saying. Yeah, so you can see the Earth's gravitational field has an effect.
Yeah. And then this is the one where they did basically pointed at kind of upwards and at an angle. And as the Earth rotated, they saw that there was a difference. So
That's pretty
the
cool.
Mach principle.
I'm surprised how sensitive it is to those changes in the. So basically, space time is different at each of the.
So neutrons know
yeah.
Neutrons know where the rest of the universe is
Exactly
at a quantum
it's
level.
like a good Mach's effect experiment, I would call it.
Yeah. So I'm kind of curious if you did a similar type of thing.
Yeah, no, my disk was just flat, totally flat and level relative to the Earth's gravitational field. It was, it was parallel to the Earth's gravitational field. That's what I would say.
Yeah.
So I didn't. If they made a spin stand that you could spin around, I would have been happy to try it. And what holds the disc on is like a vacuum chuck.
Right.
So it sticks on the thing, right?
Right.
The problem I had when I put when I tried to do the experiment on the bottom surfaces, the disc popped off.
Right.
So I couldn't do the experiment because it destroyed the disc.
Yeah. Makes sense.
I don't know if that was anything of significance, but
right.
And
I don't know if you followed it, but they were able to make time crystals. So the whole time symmetry breaking is
yeah, I know. There's a time crystal. We're living in a time crystal, is what I think.
Yeah. So really, like,
time's not linear. Like I said, it's a loop. We're in a loop.
It's not an easy
spinning. Everything's spinning with respect to everything. The Earth's spinning. The spinning around the sun's spinning around the galaxy, and that's and all. It's like, Dan, what time is it there?
I don't know. I can tell you what my clock says though.
Yeah, what's your clock say?
10:44.
It's 7:43 here.
Yeah, that's what I got. 7:43.
Is there anyone in a different time zone?
9:43.
What's yours?
9:43.
9:43. There you go. So
it's 10:42.
We're in the same time physically, but there's an offset, right? A couple hours offset. So
what you're saying though.
Everything. So, and that's what we call offset spatial diversion. Okay. And everything, even if the little stuff has that little offset. So it's kind of like that wiggle you showed in the data there, Curtis. That little oscillation. There's an offset.
Yep.
Okay, so that's kind of like we're just catching on to that. We focus so much on everything going in a straight line that we missed all the circles.
Well, and there are people who have looked at this idea of time being a kind of emergent, non-local, quasi time crystal thing. Are you familiar with Don Page and William Wooters? They worked on this the problem of time back in the 1980s, and it's been making a comeback just recently in the last few years.
When was that? Oh, there's this book I read. This is.
So are you familiar at all with the Wheeler-DeWitt equation?
You ever heard of this book? It's called I'm trying to get it here.
No.
An Experiment with Time by J.W. Dunn. He has this really cool, basically that time, it talks about telling the future and telling in the past and how it affects and he has this whole theory that's really interesting. It was
So
written.
this whole Page-Wooters mechanism thing and how this is kind of relevant to what we're talking about. Do you guys know what the Wheeler-DeWitt equation is?
Heard that.
H of psi equals 0. So it was an attempt by John Archibald Wheeler and Bryce DeWitt back in, I believe it was 1967. They first wrote this down, where they were trying to come up with a Schrodinger equation for the whole universe, basically.
Yeah, I've heard of
And
that.
it has stuff to do with like Goeth's principle about there being zero energy in the universe, yada yada yada. Anyways, what happens when time drops out of a version of the Schrodinger equation? It becomes timeless, right? So then that you end up with something that looks like that might be akin to like a static state. And so the question is, where does time come from in this? So let's bring our analogy back into special relativity and how it might break simultaneity for a second, right? So when you have clocks, right? So my clock versus your clock is going to be different depending on where we are in a gravitational well, or how fast we are moving relative to each other. That's the whole concept of time dilation, right? And so when you start mapping this stuff out on a space-time globe and doing the Lorentz transformations, you run into these really weird phenomena where things that look like they happen at the same time from one observer don't happen at the same time from another. So you need to apply a clock that's at each individual reference frame. And so then the idea here is you you can then ask, so you have the clock at one position. Let's say the clock at the boundary or the clock at the Big Bang. And so then that's your reference clock at clock equals 0. Then you compare it to the clock at some other spatial, space-time coordinate and what the clock is going to read there. And at each point, they're going to be different. Now, where this kind of comes back into the whole thing of quantum mechanics, you can add the clocks together to make a superposition of time. And then you when you add all these clocks together, this superposition of time represents the boundary state. And then this starts to get into holography, and you have equations of state and duality and how things interact with the boundary versus the bulk and things. And it starts getting really convoluted from there. But people have looked at this, and how this gets back to the time crystal thing you were saying. So if you map these all out and you map this whole superposition of all the time states, it looks kind of like a time crystal.
Hey, folks, I gotta go.
Hey.
I did post the link to the preprint article at TechRev. Uh, it's right before where Tim Ventura posted Jeremy's paper, and it's been great. Enjoyed our talk, and
likewise, Michael.
We'll see you next time.
See you around, man. On the note of this conversation, something that just popped in my head is anybody else notice that the number of reports of missing time associated with UFO encounters has dropped since we all started having the time synchronized on our digital devices instantly? I haven't heard of anything like that, and like it makes me wonder if there's some sort of temporal alteration fields being put out by the craft just to make it weird.
We have about 10 minutes left, guys. I just want to let you know, and then I can leave the Zoom up if you want, but I'm going to stop recording at 8. Oh, oops. And there's Daniel again. Okay.
Yeah, please leave it open so we can rock out into the midnight hour.
Yeah, no, that's totally cool. Brenda, well, what I'll do is at 8, I'll make you the host. How's that? And then woohoo.
You have to be a big boy host.
That's the nice thing. Zoom has a few advantages, right? I mean, one of the advantages is you can make other people the host and it doesn't, cause a lot of trouble. But like StreamYard is better for webinars, and that's why we're doing kind of our events of record on it. And then one of the other things that we're kind of challenged by is one of the reasons that I picked StreamYard, part of it was Bernie is super excited about it, right? And so Bernie got us into it. StreamYard lets you do full 1080 streams, and we don't because not all of our guests can support it. Not all the speakers can support it. But like, so one of the things that I'm always thinking of is like, at some point, should we do 1080? You know, and I don't know. I go back and forth on it, but
Unless you have something which requires high detail, no.
well, my line of thought is back when I used to do American Anti-Gravity in the day, right? When I first started putting videos online, it was like 160 by 180 or something. I mean, it was
In other words,
tiny.
god awful.
God, by today's standards, but it was
Yeah.
like that was mid grade back then, you know, and it was like 320 by 240, you know. I was like, whoa, this fits on a floppy disk. I can put 3 minutes up, you know. Um, and now by today's standards, those are trashed. So
Right. But the difference between 720 and 1080, honestly, um, doesn't look like crap. Maybe if 4K and 8K monitors become really prevalent, but until that happens, I don't think it's going to be an issue.
yeah, and that's something I stay up on tech stuff. Um, I mean, I have a 5K because I have the Apple 5K monitor. 8K is out. Those monitors are out, but they are god awful expensive. I looked at those for because I do photography. You're talking $5,000 for a monitor. Nobody will. I mean, nobody I know will pay that.
If you're a prosumer, maybe, but otherwise, there's no great benefit going beyond 4K currently.
Yeah.
In terms of price point, I've noticed like Moore's Law is pretty much like dead or slowed to a standstill in terms of like price per performance. They're like
Moore's Law
things are getting better, but they're not getting cheaper.
Moore's Law, isn't that the processor speed of computer?
Yeah, although it's sort of like generically curated to handle everything. I mean, we're talking about monitor size, but you can't get a bigger monitor without having more powerful processor, both in terms of video and CPU to pump out
True,
all those
yeah.
pixels.
And your pixel pitch has to decrease drastically, otherwise it looks like crap with huge blocky pixels.
Right. So you always have this problem when you release more and better monitors that, it's hard to find content and stuff to actually make use of it. And then yeah.
I personally think that CRTV TVs are. Go ahead.
Well, I mean, if you, I can offer kind of my 2 cents. What I've seen, and I saw this kind of coming actually, because I was writing on tech stuff. So the technology has shifted from the desktop PC market to the phone market. Phones are driving tech, and that's why when you like Apple is one of the best examples of this because they make both. The new Apple desktop PCs use the phone chip architecture, right? And they rolled that out in like 2019 or something. That's for them, it's a cost saving and architecture simplifying tool. But like some of the advantages there are you do take a hit in terms of processor speed, but they're boosting the bus speeds, and then they have a lot of specialized stuff, right? Like um, well, the way they do GPUs, the GPUs are built onto the CPU instead of being a separate board, and they're not shuffling data across the motherboard as much. There are a lot of interesting things there, right? And then
Well, the reason that they're putting it all on the die is partially for power, but mainly, hey, you want to improve video? You got to buy another box because Apple is a hardware company, not a
yeah,
software company. Microsoft is a software company, and that's why we have the ecosystem where you can plop in AMD or NVIDIA or anybody else who comes up with a really good graphic chip, plop it in the machine, and you just change your graphics.
so
Apple ain't going to happen.
what I see in the next few years is this push towards multi-processing, right? And this goes to what Brendan was saying about Moore's law is processor speeds seems like for the most part they've kind of topped out, right? I mean, the fastest you're probably going to get is 3.5 gigahertz.
No, they've gone to 5.
Have they gone to 5? Because I've seen specialty processors at 4.5 and 5, but you know what I mean? Like CAD rendering machines, really complex stuff, but the average, it looks like it's in the
Average
3
stuff is
range.
around 3.5 to 4 currently.
Okay.
It's all a matter of how much can you shrink the die, and there's how many billions of dollars is going to cost to bring up a new fab line, and then that's going to sit around for a while to recoup costs. So
yeah,
don't worry, there's more to do on that before that's a problem. There's a lot of optimizations they can do on computing.
and they've hit some real roadblocks too. One of the biggest roadblocks that I've seen has been like this thing with the metaverse, where it's like corporate America seems to keep trying. It's like they know where they want to get, they don't know how to get there, right? That's the
they see the
impression I get.
marketing that they want to do with the virtual reality overlays, and people are saying this looks like garbage. I'm not paying this money for this garbage. It
Yeah.
looks horrible.
It's also a compatibility issue. It's the same thing with the CPUs to an extent. Like the corporations all want to be the king of the metaverse in the future. They want everybody on their platform, so they're making their developer tools and all the hardware incompatible with everybody else because they want to dominate. But that's the opposite. That's not metaverse. Like whatever it's gonna be, we don't know what exactly it's gonna be, but it's gonna be something like universal and open. Well, Tim was interviewing somebody that was
going to be something like the internet.
Well,
Tim was interviewing somebody that was like, it was this versus thing. That sounds more like getting closer to the actual future metaverse than any of these punks.
So I'll tell you one thing. There were two things that were interesting. One of them we were talking about this earlier, what chat or communications tools, right? And this is because it comes down to competition. They want to own the communications channel because then you can claim the users and the whole 9 yards. But one of the problems that I see is there are so many communications apps out there, right? I mean, just look at like what's on your phone. You've got like Discord, Telegram, WhatsApp, and then like Microsoft has Teams, Apple has iMessage. I mean, you've got like the average person now has all of these Facebook Messenger, Instagram messaging. And so one of the challenges that I have, especially because like I'm trying to promote things, is like there are too many out there. And that is just a royal pain. So one thing that would be really cool to see is unified messaging. And I don't think we ever will because, no corporation wants to give that up, right? They don't want to because what that would mean would be like on the Mac, if I use iMessage, then I could connect to Discord through iMessage, right? But Discord isn't going to do that because they want you on their servers. So,
you're just going to have to do an intermediate glue layer like compilers. Here's a compiler, here's your code, and you compile it for the target. So you're going to have some kind of translator between all of these different layers, so to speak, so that it's seamless. So none of them have any institutional memory of the bad old days of competing standards, competing communication protocols. I mean, we don't have to deal with CheaperNet and coax. We're all standardized on Cat 5e, Cat 6, Cat 7, and God knows what Cat 8 is going to be. But, it's basically plug it in, don't think about it, it works. And the morons are too greedy to realize that if you have something which doesn't have a lot of friction to use, it benefits everybody.
Now,
they're bringing back the bad old days by forcing this ARM crap, and so you can't compile cross platform.
ARM or DRM?
I heard it's ARM, DRM. I think Apple's version is ARM, and the Microsoft version might be DRM. I don't know, but either proprietary chips that can You know how you have to have the right chip to run the newest
You
Windows.
have to
It's not
have the
backwards
right
compatible.
codec that's licensed correctly in order to play back content. Yeah, that's
Yeah.
stupidity.
It's dumb.
So the other thing that I see, and this one is mind blowing, right? And this, I stumbled across this last year. I'm waiting for, this is going to be one of those things that I don't know why it's obvious, but it's going to sideswipe society. So there's a company, you can look it up. It's called Hume, Hume, Hume.ai. And they developed it as an API, and you can actually sign up for free, and it might be worth doing it on their website. You can sign up for free and do some experiments with it. And what you can do is you can use their API to upload a video as an example, and it will tell you it does big data analysis and AI to tell you what the emotions of the person in the video are. Now, that by itself is interesting, right? There are a million different applications for it. But what that is pointing towards is just imagine for a moment being able to do voice stress analysis and big data matching on any video, live or canned or YouTube, and tell if someone is lying, right? And being able to do so with like say 80 to 90% confidence. And I think it was Hume. If not them, it was another one. I saw this another place. Somebody demonstrated this was mind blowing, but even with 720 video, if you have a good size picture of a person's face, it's not visible to the human eye, but there's enough change in their color that you
The
can
micro
detect their
tremors in
pulse.
color. Yeah.
So you can do pulse rate analysis, voice stress analysis, and facial expression analysis. I would bet you within a decade, I mean, you could probably do it now, but definitely within a decade, you'll have apps that'll be able to tell you, I'm guessing 80 to 90% confidence if someone is being honest. Now, just imagine for a moment, like this, that we had this political debate a couple days ago, right? Or anything, the Secretary General of the UN speaking, or I mean, God knows what, and not just that, but like husbands who aren't sure if their wife is cheating, or there are a million different applications for this. And so I don't know, it could end up being something that's regulated, but I have a feeling if things go the way that it looks like they're going, it'll be like AI. It'll be the cat gets out of the bag and then they spend time trying to fix it.
But the real question is, how does a sociopath get analyzed on that? Because with a sociopath, there's no stress, no nothing, just simply here's what's going on. And then, okay, if this AI technology can do this analysis, well, then the countermeasure is if with the presumption that a sociopath doesn't give these cues out, you have a video transform over your features to mask everything.
Could be, could be. I don't know where it'll go. I'm just looking at that initial step.
So Tim, by the way, have you considered getting what's his name?
Sorry, you're breaking up a little bit, Curtis.
There's Ethan presented, but I don't know if you've ever talked to Ray Chow about presenting. I don't know if you would.
Yeah, no,
I'm not sure
Ray
how he
did.
is now.
He presented last year, and I'd love him to present again because he's done all those changes on his idea. But I think he may be having some health issues, and so Nathan might be able to do it for him, and then
Okay.
I may end up popping a plane down to San Francisco at some point. Or what we might do is that Asilomar conference that Mark goes to, Mark may drag me along to that next year. So if we do Asilomar, that is San Francisco is where it lands. I may just go a few days early, right? And then we could save some bucks on
Is Ray
airfare and
still in
hotels.
Merced, or did he move to the Bay Area?
He's in Merced. And if I remember correctly, well, no, so Ray lives in the Bay Area, has a place, something, works in Merced. He's back in the Bay right now.
Okay.
For health reasons.
Right, right. Okay.
Something along those lines. So.
Right.
Well,
yeah,
guys,
speaking of communication, that's one of the things where he was trying to do a communication using gravity.
Let me shut things down for tonight, and I'll leave Zoom going, and then we'll roll from there. But this has been APEC for Saturday, September 14th, 2024. Thank you, everyone, for joining us today.